Been doing this Zoom business for 2 years now, and I'm still not used to seeing myself on the screen. All right, so shall we start? Can I go ahead and start? Okay. All right, everybody, good morning. Welcome back. Hope you guys got some sleep. So once again, to introduce myself, my name is Mahesh Krishnamurthy, and excellent. Yeah, so my name is Mahesh Krishnamurthy. I'm a faculty in Illinois Institute of Technology. I was just about to say Indian. Illinois Institute of Technology in Chicago. So welcome. It's day 2. We're talking about the fundamentals of multiphysics. As I said yesterday, we are kind of going through the process of defining the scope of the problem and going one step at a time. So today we're going to cover the topic of multiphysics from different levels. We talk about structural, thermal, and acoustic noise, NVH as well. So as we go forward, I'm going to include results and some of the work that we have done in our research lab. So not obviously because of constraints on time and because you're focusing everything in a 30-minute slot that took about 3 years to do. By definition, there will be a lot of details that might be missing. So if you have any questions, you want to hear anything about what we have been working on, or any details around it, please feel free to shoot me an email. There are publications that go along with it as well, but I'm more than happy to share them with you. Okay, so let's go on. So the first topic that I'm going to start with is going to be mitigation of vibration using field reconstruction. This is actually a concept that was developed in University of Missouri in Rolla, which is now known as Missouri University of Science and Technology by Professor Fahimi. And this was some of the work that I started when I was actually doing my grad school days. The reason why I wanted to introduce this is because the fundamentals of this topic, the fundamentals of this idea are somewhat foundational in my view of defining how we approach the problem of multiphysics analysis. We have actually followed through with a couple of research topics that take this several steps further. Professor Fahimi at UC Dallas has also done quite a bit of work in this area and has published very extensively. So if you want to look at references in the area of field reconstruction, Professor Steve Pekarik from Purdue, Professor Babak Fahimi from UT Dallas, and my teams have all published in this space, and you're more than welcome to look them up. Every one of us has a different perspective, a different angle of that we have taken on this topic, and hopefully you can learn something from all of them. So when you start talking about, really just to give you a brief outline of what this looks like, we're going to talk a little bit about the idea of a black box approach. We'll go into the fundamentals of energy conversion, reconstruction, and then some validation. Okay, so let's start with this. Why are we talking about this idea at all? Well, the first thing is that whenever we have done electromagnetics, like I said, the nature of electric machines and drives is that it's not a one-dimensional problem. You're always talking about dealing with electromagnetic design, followed by magnetics, and then you take it further to the mechanical structure, which means you cannot use a black box approach in which you apply voltage and current, get feedback just with the position, calculate speed and torque, and decide whether or not it's good, and then close the loop. It doesn't work anymore. It was fine when you were talking about relatively low efficiencies in the 80% maybe, but now when you're trying to get the 90s and higher, you're trying to beat an IPM that goes to 94-95% without breaking a sweat. You are trying to get every bit of efficiency you can get from this process. So the approach or the fundamental idea of field reconstruction relies on the fact that we can use snapshots of finite element analysis. The idea is, so one thing we have to remember and we have to put in context is, at no point are we explaining or are we expecting people to stop using or utilizing resources that have already been developed. The reason for that is because a lot of these structures, if used properly, can create an option for a final solution, which would be more like the co-design we were talking about yesterday, or an integrated motor drive. So this here, basically, if you look at the field distribution, this is from a 5-phase PMSM that we had designed and built several years back, almost a couple of decades back now. And what we had done basically was, the goal was look at the field distribution. You can see this is a 6-pole machine that we have here. It's a 5-phase 6-pole machine, 30 slots, integer slot. And the goal was to find out what the field distribution inside the machine is, identify the structure that enables this, and then modify this to get your best performance. So if you look at the field distribution here, what you will see is that as the flux goes in, there is a component that has a fringing effect. So typically, when you're talking about torque, how do you define torque? Like if you talk about a machine, the torque is defined as the tangential component, right? If you have force, if you do the Maxwell stress tensor calculation, you will see there are two components. You have the normal forces and you have the tangential forces. The normal forces are what give you vibration, torque, ripple a lot of times, but actually primarily vibration, acoustic noise, and tangential forces, any fluctuations there will give you a ripple, basically give you a torque ripple that shows up in your output waveforms. So if you look at the actual idea of Maxwell's stress tensor, we know these equations. They have been established for quite some time. You know that you can calculate Ft as a function of 1 over nu naught Bn Bt, and Fn is a function of 1 over 2 nu naught Bn square minus Bt square. Now, one question I would ask you is, when you look at Fn and Ft, the first thing you will notice is that you cannot influence one without influencing the other, which means if your Bn and Bt change, you cannot just maximize torque or tangential force without having a corresponding impact on your normal forces. On the other hand, what you can do is you can create a system where you give it a weight function and you optimize it for a specific criteria, because your application has a limit that you are trying to meet, which means there's a certain amount of normal forces that you are able to withstand or you're able to allow in your system. And based on that, you can calculate what the torque is going to be. So torque is given as R cross F. We know that. I mean, this basically the radius times the tangential force. So you can calculate the overall force, look at the field distribution, define the individual field components, and from there start your optimization. So the mitigation of vibration really is applicable in a bunch of places, right? You're talking about aerospace, automotive, military, naval. That's just a starting point. Now, even things like your air conditioner, if you want to talk about an HVAC application, which for the longest time, HVAC was limited to industrial applications or residential applications, right? But now you are talking about systems like data centers, agriculture. Here, I would imagine if you go to rural places, it's not as common. However, if you go to the larger companies for barns, if you want to maintain optimal temperature for maximum productivity for the animals, there's actually temperature control spaces even for your animals for your to be kept, right? So the idea of maximizing or optimizing how much energy you are consuming has very substantial benefit. If you get acoustic noise, if you get vibration, one thing that can happen is, think about an HVAC system. Let's say you go to a gym and they have a rooftop, an RTU, basically a rooftop unit that is set up, and it has a blower or fan that is sending the air through for the centralized AC. The challenge you will notice is that if you end up having acoustic noise on your rooftop unit, what you're going to do basically is you have a metal conduit, right? The entire piping system is made out of metal. So I know our mechanical engineering folks are not here right now, but what happens if you actually end up sending metal, or if you have metal ducts with vibration acoustic noise? You will start to resonate across the entire building, and you'll basically create a giant speaker in your entire building, right? It will carry everywhere in your building, and that will be very nasty. So the application or the relevance of issues like NVH have been very, very real. So if you look at this one, this is just, like I said, it's a 30 slots 5-phase machine. And at that point, one of the things that we were always trying to do well was trying to make sure that the meshing was done right. At that point of time, we have over the course of time used different simulation software. And one of the software I grew up using was called Magnet. It's by a company called Infolitica, which then got bought over by Mentor Graphics and then by Siemens. I believe now it's Siemens now. I used this software for a very long time, and one of the challenges that I found was the meshing. And that's not the reason we moved away from this, but the challenge of creating something like this, when you are looking at the microscopic this definition of magnetic field required you to have a uniform mass distribution. Otherwise, the calculation of your fields that happen in the middle of the air gap were not accurate, and more importantly, were not reproducible. So just looking at this, this is the field distribution, and this is what tells you how the system works. You have the fringing that happens. If you don't have any flux, the first thing you will notice is the field uniformly distributes across its zeta pole. So if you look at the tangential forces, your tangential force basically will primarily try to cluster around the tip. So when it goes to the side, that usually happens because of the fringing that you see in your slot. So if you, the more this fringing is, your flux is basically going to flow in that direction, creating a tangential force that allows you to create that torque. Now, this is the field distribution that you have when you have one more have an animation. Okay, so this is the field distribution you have. It's a uniform field distribution. If you span across one full pole pitch, what you will notice is that you get a very uniform magnetic field distribution. FT and FN are very uniformly distributed across the entire pole. And I actually have, yeah, there is a field distribution as well, flux distribution that goes with it. But so this is basically for in the air gap. So this calculation was done in the middle of the air gap, and what you're seeing basically is 0.1 millimeter outside the stator, inside the stator, and 0.1 millimeter outside the stator. So we basically looked at two layers, one just outside the stator, one just inside the stator. The reason for that, or the outside and inside, the reason for that really was we wanted to establish the idea of a continuity theorem, right? I mean, you have, you know, if you have done FE analysis, if you've done electromagnetic analyses, you would remember continuity theorem, right? Normal flux flows through, tangential flux actually changes. We'll talk very briefly about that, which is this one. So what this basically says is that continuity theorem tells you that going through the air, if you go from one material to another, if you go from M19 to air, your normal field stays continuous. So it goes from one medium to another, there is no change. But if you're going on the from tangential component, your field intensity, the H, is what actually stays consistent. So all you have to do is you have to calculate, because your mu changes, your permeability changes. Based on that, your B will change as well. So depending on what permeability you have, you will get a new value for B in the tangential direction. So what this basically means is that BT in M19 and air is the same, but if you talk about the tangential force in the steel, that is given as 1 over nu naught times the flux distribution in the air. Okay, so the math here is fairly straightforward. You can create a simple equation. The way your magnetic flux inside the electric machine is kind of broken down, it gives you typically N and T. You might have to decompose. When you're doing this calculation, you might need to decompose your fluxes into XY component and then reconstruct back to make sure you have the right components when you add. Keep in mind, when you're adding them together, they have to be in the same direction. If they're not in the same direction, by definition, normal fields cannot be added, right? I mean, normal forces cannot be added because they are all in with respect to the angle. So you can add the tangential components because they're all in the same direction, plus or minus basically. They are going along the tangential direction, but the normal components cannot directly be added. So when you change the, look at the air gap flux, the field distribution inside the air gap, one thing we notice that in the air gap, the field distribution is not the same everywhere in the air gap. We established that at the beginning when we talked about the idea of fringing and how the field actually concentrates. That's also one of the reasons why you do end up creating localized hotspots. So this is essentially just outside the zeta pole, just outside the rotor, and in the middle of the air. When you look at all three fields, there is an actual difference in the magnitude. What this also means is that you need to know where you are going to calculate your field distribution. If you are using flux density as your function to establish the forces that are present inside your motor, you need to have a reasonably good understanding of what the fluxes are and where you are probing your model. Now, when you apply excitation, one of the things you will notice at the very beginning is your field starts to deviate, it starts to change direction, which makes perfect sense. Essentially what you have is you have two magnetic fields, one from the rotor, one from the stator. They both interact and they give you a resultant field. Logically, it makes perfect sense. Mathematically, you just have to make sure that in the analytical form, you are looking at it with the right idea. So what this does, of course, create is if you look at the flux, you will get localized hotspots. Now, this is numerical error. You don't have to worry about that. But your fringing now becomes uneven. So when previously you had equal fringing on both sides, now your fringing at the radial edge actually becomes different. Now, if you look at the change in flux distribution from the, yeah, okay, good, I have this here. So this is what you had, the flux distribution in the air without without any excitation. And you go from there, you actually change it. And when you look at the same layers, when you apply current, because you have applied current, your field distribution starts to have a different profile. Once again, it makes sense. You are talking about fields that basically are two separate fields that are interacting. So the fundamental question we were asking in this specific project was, can we use an idea like superposition principle, like what we do for circuits? If we have multiple sources, we calculate the current from each one of them, and then we superimpose them. Can we use that same idea in this method? And if so, how many ways can we do this? Do we need an impulse response? Do we need a current response to this? What kind of a system do we need to recreate the idea of individual sources, so that whenever you add a new source to it, you don't have to redo the entire simulation? You only have to integrate specifically what the role of that specific source is, and that will allow you to save time. So if your flux density is not going to change because you have permanent magnets, that means all you have to do is you have to resimulate your current functions. So recalculate the function, the field that comes from the current, and add that to the permanent magnet flux that has been constant this whole time. That will be time efficient, and it also gives you results for an iterative design that can happen much faster. So this once again is the force distribution over one pole pitch. You will notice basically is that not all the poles see the same force. We have to remember that. Just because when somebody says average torque is something, average comes from something. Average does not tell you that every pole is going to see the exact same number. By definition, every one of them has a different, because you are placing your magnets in a certain way that the orientation of the magnet directly aligns with the pole or the phase that you are trying to energize. So this is the basic idea behind field reconstruction, is that if you have a current carrying conductor, you have a permanent magnet, in that case you can change the direction, or you can basically estimate what this field positioning is going to be with respect to the magnitude of current that is applied to the system. And you can define them in terms of what's called basis functions. Basis functions are like a unitary function in which, if you remember, once again, when we did superposition, we would say for if you are trying to do for 5 volts, let's calculate the unitary function for 1 volt, and then whatever the voltage is, we will just multiply it by that time. That's the same idea. We don't care about what the field is, because if we have one distribution for one geometry, we know what that's going to look like. Now we can recreate it for the same geometry with any current. So the assumptions of field reconstruction that we did assume at that point, which now actually has gotten further. I know Professor Fahimi has done some work on saturation also, but in my case, we had looked at no saturation. We took it another direction. We took it to acoustic noise, which I will talk about later today. We also ignored the impact of eddy currents. Surface magnets were basically is what we used. They were surface mount PMAG machines. So actually it's convenient. So one thing is, if you're talking about the idea of basis functions, the first thing that you would remember is that I said each current applied to the system gives you a certain amount of field. What that means is, the first question you would perhaps want to ask is, how does that look like with changes in geometry? The first thing we did was we did several simulations specifically to analyze what the impact of the slot geometry, the coil placement, and the rotor on the back itself is. So if you go one at a time, so we actually added a slot to it, because at that point the question was, how accurate is FEA? You had to bear in mind a lot of work has happened since then, but this formed the fundamental idea. Before I did my PhD, there was another PhD work that was done from Missouri University of Science and Technology. I believe it was by Professor Weidong Zhu. That was one of the first works on field reconstruction that happened in the country, so to speak, if not all across. And it was co-supervised by Professor Fahimi and Professor Steve Pekarek, who are now at Dallas and Purdue respectively. So the same idea, what you will see is that if you start adding more slots, each individual pole starts to show, if you're looking at the magnetic pole, they start to show the impact of the slot, the presence of a slot. It's not uniform like it was before. where you have one slot and the rest of it is 0, adding the slot, adding each one, every single geometry adds to the presence of your flux. The same thing happens even on the tangential side as well. This is the X, because this was not a rotational, or it was not a radial geometry. So for a Cartesian system, this was X and Y, gave you a clear indication of the fact that you have presence of a slot. The same thing, two coils, you see two spikes that go up and then in the negative direction. And if you look at the BY, once again, it says that, shows here that all you're doing really is you're recreating Ampere's law. It just tells you, right? I mean, you have the right hand cross rule. So you basically say current in one direction, flux is going in the direction of your remaining fingers. It's basic electric circuits, or electromagnetics even. So that idea is very relevant for electric machines. And the point we were trying to emphasize with this research also was that electric machines has a lot more fundamental knowledge that is involved. It's not just about using FEA and experimental results. There is a tremendous opportunity for creating outcome specifically based on our basic understanding of electromagnetics. So this is the overall profile of how we do field reconstruction. You first create a normal and tangential flux density for current flowing, 1 amp of current flowing through the structure. You determine the basis functions for that. From that, you go to the initial geometry, and of course you have the permanent magnet and the stator, two components. They both meet together for a position, and that's it. This is all you need. You need one of those for a given slot current of 1 amp, and you need one snapshot from the permanent magnet, and then combine them together and you start reconstructing it. What this does very quickly for you is you can actually define what your current, the optimal current for your system needs to be. So if you know what you're trying to optimize it for, you're trying to get the maximum torque, the minimum radial force, depending on the application, you can define what this is supposed to be. At that point, we were trying to work towards quieter operation. This is these are the components specifically defining the analytical function. You have the magnetic design, and then you have the permanent magnetic contribution, and then you have the external excitation. So when you do field reconstruction, we have a model of the PM machine that we had created. This was a, if I remember correctly now, it was a 2 kilowatt drive is what we had, and that's a field reconstruction. Now this is a four-pole three-phase machine, 12 slots. And what we did basically was, this is just the response from, this is a slot effect you're seeing here that we had established from the previous case when we had extra slots, and BN and BT for unit DC current, 1 amp of current applied to it. So in terms of the pole pitch, if you look across the pole pitch, you rotate this, the entire orientation in space, and you keep adding them to B. All you have to do is keep rotating them and add them, so you can go from one single coil, one phase excited, to getting an idea for the entire pole pitch. You don't have to recalculate for every single phase, because like I said, it's a symmetrical machine, which means if your rotor position changes, you only have to account for that orientation change, and that allows you to recalculate. And you're comparing FEA with reconstruction, and they match exactly to every last point. The same idea, you rotate each one of these pole pitches, all basically for 3 phases at 120 degrees, and now you have the distribution for the entire machine. So with that, you have now with one single static FEA, which by the way, the reason why this is also relevant is because if you're trying to do a co-simulation in which you want to integrate your magnet or your FEA model into Simulink or PSIM or any circuit software, you cannot do a full transient SEA. I mean, you can, but it takes a long time. So yeah. I appreciate it. Thank you. Definitely. So what you're looking at here basically is, this is specifically reconstructed FE results for normal flux density for a single phase. You rotate them in space 120 degrees and add them all. This is the reconstructed FE analysis results for 3 phases. So like I said, what the benefit here is now is that you did static simulations from FEA, and you got the results, converted them to a single pole pitch, and from that you took it to 3-phase, and you integrated that right back into your Simulink model. Now that gives you a much faster response to optimizing, let's say optimizing your current. You can either reduce acoustic noise, vibration, field distribution, basically whatever you want to do. So what you have here essentially is you have the reconstructed FE results from current in 3 phases, add the flux density distribution from the permanent magnets. That gives you the overall field distribution in the machine. So the idea itself sounds more like, of course, we should have known that, but it was simplistic enough to where it made sense, but it has still not been done from the perspective of machine design. So this was one of the early works that happened in this area. So with that, I'm going to open it up specifically to questions. There's quite a bit of results, and I think I'm keeping straight on time right this time for a change. So I wanted to open this up to questions. When you were talking about electric machine design, several of you have done quite a bit of work. Yeah, you have a question?
I just want to ask that graph, we can observe the dip in the middle of that curve in both single and for three.
Yeah.
What is the reason behind that? Why we are getting that little dip? Yes,
so you are so now what you have is you have slot effects for every one of them, right? So every one of the slot effect will start to be visible, and that's actually the fact here is that your flux density it's a very observable system, which means if there is anything on the input that changes, your field actually shows you what change in the geometry has happened. So let's say hypothetically, if one of your field distribution, let's say one of your slots was unevenly designed, it normally should never happen. But if that was the case and you had an asymmetry of some sort because of a design error or manual error, then this would not be symmetrical. You would actually see a bigger dip. So what you're seeing here, these are all the slot effects. So if you draw that line down, this is the presence of the slot. We are energizing all three phases, right? I mean, it's a PM machine in this case. So we were energizing all three phases, or for the BLDC, 2 phases, and then one is the silent unenergized phase. So what you're seeing here basically is all 3 phases energized and the effect of the slot.
What will be the reason of mitigation of one of that dip in the 3 phases?
So we're not trying to mitigate the slot because the slot geometry is something that exists. You can change the slot geometry. What you're trying, in our case, what we were trying to do was we were actually trying to minimize normal forces. So that's perhaps one distinction I should make is that oftentimes we combine the idea of flux with force. It has a direct correlation. Flux directly leads to force generation. However, in most cases, we are trying to optimize force. So that means that you are trying to reduce your harmonics because that will directly have an impact on your overall system performance. But other than that, what you're trying to minimize is not the flux distribution. So you can take it one step further in the design feature. You can optimize the slot geometry to make sure that you are getting the least amount of FN, for example. So in that scenario, you're not trying to minimize this still, you're trying to optimize it. But that optimization is not a real number. I cannot tell you that it should be smooth. It won't. It just won't. But you can get it to a place where your normal force distribution in the machine is going to be as low as possible. Does that make sense at all? Okay. So with that, I mean, like, please feel free if there are any other questions, but I also wanted to open this up. When you're talking about vibration acoustic noise, we will talk about this in a little bit. I will bookend this. Actually, we'll start off with this field reconstruction. We'll go into a little theoretical concepts, go into NVH, acoustic noise, structural design, and then we'll roll right back down into using a method like this, specifically at the end that we have done for surrogate modeling, when we talk about an overall design framework for electric machines. So what do you think in your mind, if you're talking about the experience automated analytical process in which you basically know what you're supposed to be doing, so user experience matters, right? So if you have the option between this or an iterative solver driven approach in which you have FE analysis, you did the analysis, you got the right results, yes, no, you go back and redraw again. In your mind, what do you consider to be more effective? And this is just an open-ended question. If you don't have a thought, that's perfectly okay. But I wanted to see what you thought about any of these approaches in the context of an overall machine design, thermal, electromagnetic, and NVH. Any thoughts? Any experiences that you might want to even share for that matter? Then hold, if there are no specific ideas on that, hold your thoughts. Maybe at the end when we talk about the design framework for the entire electric machine, I am very keen to hear what you think about the entire idea. So this was just a starting point. All right, so let's move on to the next side of this conversation, which basically was the multi-physics nature of energy conversion in electric machines. And the reason I'm talking about this is because when we talk about drive design, when we talk about multi-physics, usually what we're talking about is losses. We should be okay in time, right? Yeah, we're doing just right. So When you talk about electric machines and you talk about electromagnetics, we are essentially talking about losses in the machine. So losses are by nature going to happen, right? It's an essential component of physical systems in existence. So if you talk about the idea, what we know is that motors are going to be around everywhere. We can optimize the design of the electric machine for its overall performance, or we can look at individual components of what it is that is going to be your most challenging problem. Here's the reason why. Let's say you have an electric motor, okay, and you want to create a system where you want to minimize the amount of acoustic noise going from the motor into the ambient. Okay, so obviously vibration and acoustic noise causes losses. We know that. But the question is, what bothers you more? Is the loss percentage, is it high enough to where your efficiency is going to be affected, A, or B, is it that the acoustic noise and vibration is inconvenient enough to where your product might not find use in the industry? Because there's two angles, right? Your efficiency drop might be, let's say, 0.5%, 1%, and I'm throwing numbers out there. If it's a 0.5% to 1%, does it make a huge difference? Some might argue yes. But generally speaking, if it's noisy, you're definitely not going to get it, right? I mean, if you have a vibration, if you're driving your car and you have a power steering and you get a vibration, a ripple that basically comes to your hand, you're not going to buy it. If you have ever sat in a car that is going really fast, you will see that the steering moves quite a bit. That's from the road reaction. If your motor added to that force, your control, the ability to control will be dramatically worsened. Right? So it's a very important component. So we need to look at the idea of generation, transmission, and conversion of power. We cannot think just of how my motor behaves. We have to think about how the motor behaves in the context of the overall application. If I reduce acoustic noise, what am I doing to the thermal behavior? Am I reducing that as well? Because the modes of transfer of your noise to the ambient is very similar to the modes of transfer of heat. So when you're basically designing a machine, if you're trying to extract heat from the coil winding, you're sending the heat over to the surface. You have fins and whatnot, but it basically is a contact-based system, right? So at the same time, if you start to separate them out, you give it a little bit of space between the housing and the stator back current. Arguably, you could get a lot less acoustic noise because there's a spacing. Problem is, you'll also have lower heat transfer coefficients, right? So the heat transfers in a similar medium to sound, which means you might end up having to optimize or select which one is more important, or how you are going to optimize within your tolerances. So the two, oftentimes when you look at the magnetic fields, if you see them, we think they are both mutually exclusive. However, that's not the case. The fields that you see inside the electric machine really are very much integrated. And we're going to talk about magnetic fields. And essentially, when we talk about electric and magnetic fields, we're going to look at what does that mean? Because once again, when you go into high voltage application, we talked about this yesterday, we start looking at ideas like partial discharge, right? I mean, electric fields are not a problem until it's a problem. So if you look at this is going back a little bit, perhaps for a lot of you, this might be tried and tested, you know the basics of this. There is a very inherent interdependence between electric and magnetic fields. So electric fields comes from charge. Magnetic fields comes from flow of that charge, current. You have electric fields can be shielded, they can also be weakened. Magnetic fields, not so much. So that's the difference there. If you have opposite polarity of charge, they attract. If you have similar forces, repel. Your presence, the potential difference that you have is also known as electrical pressure. H is magnetic field intensity, is basically magnetic pressure. If you talk about group of charge moving, it's current, and current is measured in amps. When your charges move, they create a magnetic field, basically the current. So charges move, charges create electric field, charges move, they create magnetic field. The same charge under different circumstances creates an electric field and a magnetic field. And that basically creates the lines of force. We know that what they are, field distribution, we just talked about that. And the strength, if we move away, that's universal truth. If you move away from it, it gets quieter. So just to give you an idea here, I think I've every single class I have ever taught, I think I've always mentioned this one. So to give an idea, when I was working at a company towards the end of my PhD, we were working on high voltage plasma for generating for getting hydrogen. This is a while back. So we were looking at specifically getting hydrogen from ethanol. So we're trying to create an ethanol reformer specifically to get hydrogen from it, because at that point, hydrogen infrastructure was heavily in development, and there was a lot of emphasis on it. What I realized was when I was running my system, we had 20,000 volts. We had a 20 kilovolt plasma that was going on the side. We had electrodes that were basically sending out for about a half-inch gap. I was creating 20,000 volts plasma. I had my converter built and I was sending out pulses, and that was breaking down the ethanol to give me hydrogen. The math, the method was okay. The delta H, about how much energy I spent versus how much hydrogen I got, that's a whole other conversation, because that is overall system efficiency. Let's not go there. But the important part here is when I was working on the project, what I realized is that my this is 2006, 2007. So this is a long time back. For a lot of you guys, you were way younger. So what I noticed is that on my computer, my screen, when I was running the plasma, my screen started scrolling on its own. Can anybody tell me what happened? What might have even happened? And while you're thinking about it, let me get a bottle of water. EMI. So where would you think that EMI coupling happens? From where to where? Where could you think? Also put in context of the year. I specifically told you what year it was because it has relevance. Well, it was not that old. It's not a CRT based system. You're very close. Correct. We had the monitor was still LCD, so we had LCD monitors by then. So thankfully we did not have CRTs, but you're right there. So it was, we found out what the problem was. It was not exactly the CRT, but what else could it be? No. Actually, the CRT thing was another one of the my examples that my professor had given me when we were students in a course called Grounding and Shielding, where he worked for IBM and they had construction going on, and they spent a ton of money trying to figure out why their monitors would flicker when you had to degauss a system. Remember the CRTs? Oh, most of you guys would never have used CRTs. But in CRTs, you had to press a degauss button. It would kind of do a big blink and kind of dissipate all of his stored magnetic field. And they spent a lot of money only to find out that they were getting EMI, and all they had to do was replace the CRT to an LCD, problem solved. Lots of money later, that's the answer they got. So that was, so similarly, what we found out was I had a PS2 mouse. PS2 mouse. I had a serial mouse. I did not have a USB mouse. So not even USB. I actually had a wired mouse. So I tried everything. I put a choke on my wire there because I knew it was an EMI issue. I even put foil on it to see if I could create a Faraday cage around it, shield everything. And all I did, all I had to do at the very end was switch from a wired mouse to a wireless mouse. Problem solved. That's tough. So what I'm trying to say is that when we're talking about electromagnetic fields, a lot of times the problem is not as complicated as we try to make it out to be. Sometimes it is, but sometimes it isn't, and it's very important to remember your fundamentals. We know what magnetic field intensity is, we know what magnetic flux is, and field density, right? H is equal to Ni over L, number of turns, current, and length of conductor, and of course you have permeability as a function to define your magnetic flux. We talk about the permeability, and you have to define relative permeability. For machines people, it is extra important because mu r is a real number. And the reason we use mu naught is because mu naught gives us permeability of free space. And combine that with mu r, which is relative permeability, numbers are not unwieldy and huge. So that allows you to keep numbers in the above 1 in most cases. So if you combine all of that, you end up getting an equation that defines your flux, which is mu naught mu r Nia over L. Another definition that we need to know, for if you haven't seen this, is the idea of reluctance. This in particular has substantial relevance for motors like switch reluctance machines. We will talk about that on day 4. And there you have to look at the idea of generation of inductance. You need to know what qualifies as inductance. If you do if you implement methods like vector control or field-oriented control, you will remember that we actually talk about concepts like ID, IQ, LD, LQ, right? We are talking about direct and quadrature. Where what we're trying to do is we are trying to make the AC machine look and behave like a DC machine. We are trying to decouple the component that creates back EMF and the component that creates torque. We're trying to separate them and make it look and behave like a DC machine. So torque and back EMF are unconnected. But for getting there, you need to know this fundamental. If you don't have a basic idea of how L is included or calculated, you might end up with a situation where your overall methods are incorrect. So basis for transformer action, motor action, generator action, you've seen all of this in your undergrad classes, quite possibly, energy conversion and such. You essentially have a coupling that happens between two coils, one coil to the other coil, and that gives you transformer. If you have a force, you have two magnetic fields, they attract or they repel, that creates a motoring action. And if you have a prime mover that has a mechanical force that causes the magnetic field to change, and that field couples with the coil, you induce voltage. Now we're going back to Faraday's law. Moving magnetic field, stick a conductor in there, you get back EMF. So the ideas of motor performance, motor action, the point I'm trying to make with this is that they're all similar. Every motor has the same basic function, the same basic method of operation. It is a conversion of energy. I'm talking about conventional machines as it applies to higher power. If you're talking about variable capacitance and all that kind of stuff, that's different. I'm not talking about the ones that work on electric fields. That's a different definition. So here, if you're talking about a generator, you have to make sure you have a field that is present, a static field, and you have a prime mover that spins your machine to create that time varying magnetic field. So like I said, the induced voltage from a time varying magnetic field is given by Faraday's law, and then you can have I dot L cross B, which basically gives you the induced force on a wire. These are the basic equations that allow us to define what multi-physics systems are going to look like. This is an interesting concept because oftentimes when I am talking to anybody who's new to this to the research space, it's difficult to visualize what intensity, density. We use those phrases very comfortably as if everybody's supposed to know that. Magnetic field density, magnetic field intensity, flux density, and we use them interchangeably sometimes without necessarily caring for whether or not the person in front remembers it. So a better way to perhaps frame this is comparing them with an with a magnetic or a mechanical system. So voltage, electromotive force is the same, is analogous to magnetomotive force, which is torque in a rotational system. In a linear system, that would have been force. The idea basically is what is the cause, what is the effect? In an electrical system, which is the cause, I always ask that question, I get varying answers. Look at the outlet in your wall. Can you get current without having voltage? No. Why? Because there is no potential difference. So voltage can exist without current, not the other way around. Therefore, voltage is your cause. EMF becomes your cause. The result of voltage is current. Result of MMF is flux. Result of torque is speed. The presence of basically the presence of action from that applied force is demonstrated in the form of speed, not position, because position is, as relatively speaking, it's a static piece of information. Speed tells you whether or not there is an actual impact of the force applied. You have the flow is opposed by resistance, reluctance, and in a mechanical system by friction. For energy stored, you have inductance, diffusion constant, and inertia, J, basically Newton's first law. It essentially continues to stay in a state of rest or motion, right? The last one, the magnetic system does not have an idea for, is where you can store voltage. We don't have necessarily a mechanism for, I don't know that we have mechanism. Arguably, you can talk about permanent magnets, but that doesn't store, it just has it. So there is no good definition for what capacitance could look like that I could find. But here it is spring constant, so it stores the motion in the system. So if you look at the electric and magnetic circuits, you have the equations that are defined here. Now, this is where we actually start to look closer into electric motors. How many of you have never seen this? Most of you probably have, but how many have never seen it? Okay, I don't want to put you in the spot after having put you in the spot. But what I'm trying to say is when you look at magnetic field, when you're designing an electric motor, you need to know what material you are going to select. The basis for that selection are oftentimes twofold. One, you have to know how much money you have. That always cuts down everything into perspective. You can talk about mu-80 hypercore 50 alloy. It's going to be 6, 7, 8x the cost of M19. More than likely, your company will say, yeah, no way. We're not doing that, right? So you might go for exotic materials of any other kind. You create alloy, you do chemical vapor deposition, you create systems. Those are not going to be easy either. The reason for that is essentially what we're trying to accomplish. We're trying to go from a region of low reluctance to a region of high reluctance. And we're trying to make this gap as much as possible. The idea being, I want to apply a lot more current before I generate heat. Why is that? Because This is my cause. Remember we talked about voltage current analogy. This is my applied input. This is my measured output. I want higher B for low H. I don't want to apply any more H than I have to. So if I keep increasing it, the sharper my curve is, the happier it makes me, because I can apply a lot less input and get a lot more output. But the problem is, if you start applying too much and you end up into what's called deep saturation, where your numbers are here, you are now applying more input, but the output is flat, which means you are getting a very small change in your output magnetic field. As a result, that energy has to go somewhere, and it shows up as heat. Right? So that's the first definition of what limits your choice on the materials. The second thing is, this is basically called the hysteresis curve, right? So if you are talking about the electric motor, let's say an AC machine, in an AC machine you apply AC, you have positive and negative voltages, which creates positive and negative currents. When you do that, you need to know that you actually, when you energize it, it goes to, initially there's a line in the middle, right? That's that line here. It goes up, but when it demagnetizes, it never goes back to zero when you remove the entire magnetic field. It goes back to this number that's called remnants, BR, right? So it goes back to BR, or magnetic resonance, remnants. In order to eliminate that entire flux, you have to apply a negative current. So you actually have to apply a negative current. Keep in mind, H is a function of N dot I. So it's a function of ampere turns. The more current you have, the more, so you're going to apply a negative current to extract this energy. An example or an analogy for this would be, imagine you're talking about a sponge in which you're pouring water into it. So when you pour, initially the sponge is dry, you can pour water, all the water gets absorbed. At some point, the sponge starts to saturate. At that point, when you pour water in, the water just seeps out, which means now you're going to have a lot more losses. All that water never really gets stored, right? If you actually essentially squeeze it dry, sure, to some extent, or even if you leave it there, it will start to dry up. But by on its own, it will never release all of its stored water. You actually have to apply another pressure, external pressure, to eliminate the stored water, because it will actually store some water into its pores. Magnetic systems have a very similar concept in the form of magnetic dipoles, the magnetic domains. They energize themselves. They store the energy in the form of an alignment function. So the more they're aligned in the direction of the magnetic field, the less loss you're going to see. But at some point, all of those domains have been aligned in the same direction. And in that scenario, you end up creating losses. So this is just the idea of reluctance, how you would look at it. This is the simplest electric machine you can think about with a C-core transformer. You can apply voltage. You have two. You have the core reluctance, and you have the reluctance from the air gap. Based on that, you can talk about, in a lot of cases, we can ignore fringing because we don't talk about fringing for simpler calculations for the initial design. This actually leads to the idea of what's called MEC. I don't know if any of you guys have worked on MECs. It's called magnetic equivalent circuits, in which you represent the entire magnetic behavior of the motor in the form of an electrical circuit. It allows you, once again, so everything we're doing, keep in mind, the benefit of being an electrical engineer is everybody's trying to use what we know very well. They are trying to convert everything that they know into an electrical circuit equivalent. So that gives us a substantial benefit. If you look at a coil adds to the same thing, you end up with calculation for inductance, which means now your number of turns has a direct relevance to what inductance you're going to get. This is very important for motors like switch reluctance machines, where the number of turns has a significant impact on the inductance you're going to get. If you talk about losses, one thing is that this figure you probably have seen in a bunch of places. If you look at the input power minus the output power is always losses. Whatever you didn't get at the output is lost. We have stator copper, stator core, rotor copper, rotor core, stray, and mechanical losses. Stray losses usually are numbers that we put a percentage on. We don't directly calculate them because they are in the single percentage range. We put, usually if you look at your calculation, they will say assume stray losses to be 1 or 2%. We're always trying to minimize this number as much as possible. So that takes us to what this looks like in our losses. Why is this multi-physics? Now we are moving into the realm of thermal. So if you look at the idea of a current carrying conductor, we know that the power is lost because of resistivity, which means your copper loss is given as I square R, and that is a function of your current density, right? You have to know how much heat you are going to generate in a given system. it is surprisingly important to know how you are calculating your input impedance, your coil winding resistance, because that really will tell you how much thermal management you have to install into your electric machine. So in terms of the uniform current distribution, one thing you have to remember is that as your temperature changes, so does resistance, because your electron mobility changes. When that mobility changes, you also have to account for the fact that if you have variables in your system that are, let's say you're doing sensorless control, and you are assuming a certain Ri plus L di dt equation, and your temperature in the system changes quite substantially, then your R is not going to be what you thought if you are measuring at 25 degrees Celsius versus, let's say, 95 degrees Celsius. Let's say you're going to peak power for traction. Your R might change, which means you have to have an awareness of what happens. The new calculation of this value of R new has to be a function of the thermal coefficient. So alpha is the thermal coefficient, the temperature coefficient, and the that has to. So this is your original temperature T0, and then you can calculate the new temperature, because based on the new temperature you can estimate what your resistance is going to be. So it's not just that resistance is needed for temperature calculation, it's also the other way around. Temperature actually needs to be used in your controller oftentimes when you are trying to define the maximum resist or your the effectiveness of your controller. It is just like as if you are going from most of you guys have done converters like buck converter, boost converters, right? You've seen them usually somewhere. When you go from continuous conduction mode to discontinuous conduction mode, what you will notice is that your waveforms change, but more importantly, the average value of your output voltage changes a ton, right? If you are not expecting a system to go into discontinuous conduction mode, what happens? Your math doesn't add up all of a sudden, and you think maybe a circuit's broken. I've had that happen when I was working. I was expecting the voltage output to be a certain value. It turned out to be a lot lower. And I had to go through my entire calculation to realize that my average current was too low for the frequency I was selecting. So I had a very low frequency. As a result, my current would actually drop nearly to zero and push me into discontinuous conduction. So ideas like that can happen. You can actually introduce an error into your temperature estimation or into your resistance calculation because overall your operating conditions changed. Okay, so in terms of losses in copper losses, you can define the idea in terms of skin depth and proximity effect. The ideas are simple. Skin depth. Does everybody here have you come across the term skin depth for high frequency components? Skin depth really is the amount of surface area, amount of your conductor where your current flows, right? Higher the frequency, the smaller that area is going to be. Why is that a problem? It's a problem because we designed the conductor to carry the entire current. If I end up getting into a system where 60% of my conductor never sees the current, then I square R means my I in that small region is very high, which means I square R is going to be substantially higher. So my heating in my conductor will be a lot. As a result, what do? If we end up in high frequencies, we usually use standard bundled wire, right? We actually break the conductors down, and that we will talk about much later when we talk about the design. We will talk about it in terms of what to talk about, like Litz wire and that kind of stuff, how we use thinner wire, thinner conductor. All of these are interconnected. So proximity effect is basically your eddy currents that are created because of current flowing in the adjacent conductor. Skin effect is because of current flowing through the same conductor in itself. It creates a difference in how much of the current is flowing through or how much of the conductor is handling the current. And here it is going into proximity effects. So like I said, one thing is relatively very impactful these days is the use of Litz wire. So Litz wire basically, I will talk about that, copper with an enamel coating. So it's a different kind of wire, still copper wire with a different kind of reasoning for use, and it's specifically used to suppress eddy currents because it also has a twisted connection. So the same thing can happen also in your core. So we actually have an article that we have published quite some time back, which looks specifically at the idea of magnetization. You can have a similar, this is for your eddy currents that are present inside the core. And this is based on you will see that the middle of the motor does not see. This is the current density inside the machine. So what you're seeing, the surface current density. Keep in mind, eddy current is a surface phenomenon, which means in order to reduce that, what do? We laminate, exactly. So all of you guys are very good at this idea, right? So the thinner your lamination, the lower your eddy currents are going to be. And the benefit is, of course, that you're going to have low losses, but more laminations means more money. I think my mouse stopped working. Yeah, I think. Yeah, the battery might be, that's okay. I'll use this. Okay, so eddy currents, like I said, so you essentially you can create this lamination structure. The lamination structure allows you to go into multiple cores. If you're talking about the lossless electric machine, you are talking about space harmonics. If you look at the eddy currents, one of the things also you get is things like slot harmonics. You have the use of NdFeB, neodymium ferrite boron, which has a high conductivity that creates a lot of eddy currents. So you can also create a partitioning in your permanent magnets, but that has a cost. You actually have to work through the consequence of it. So I'm going to essentially, I believe this should be the last where I'm going to stop, or I'm going to finish this session here, is in terms of the losses, you have mechanical losses. These are intuitive losses. We have friction and windage, and then you have specifically in terms of requirements that you have for bearing impact that have a solution impact on the life of the bearing itself. Yeah, sorry. Mechanical losses can have an impact on things like bearing life, speed capability, precision, ability to cope at high temperature, and of course, then you have important operating conditions where you have to look at load, speed, temperature, lubricant, and such. So just to look at this, if we are trying to stay on course, what do you think in terms of, if you talk about different motors based on the machines you have selected, what do you think in terms of, so there's the options, right? The first one we all talked about, laminate them. Great. What else? Has anybody here looked at the idea of something like optimizing your flux manipulators or flux barriers, in which you change the geometry within the stator or rotor? Are there any thoughts or ideas that you have found to be very effective in doing something like this?
So, by rounding the corners of the teeth, I once done that part in my MTech, and little
it's a very important point. In fact, if you go, it's a very good thing you mentioned. As a matter of fact, we are working currently on some ideas. There is an approach called kernel-free boundary integral method. It is a concept that is used really in the space of fluids. So it's very popular for fluids. It was developed by in collaboration with one of my colleagues from applied mathematics. So it's a very magnetic intensive paper. We have a paper due for that and one published. But the idea actually is that when you're talking about fields, the biggest challenge, even for FEA, that comes oftentimes is sharp edges. So first and foremost, your analysis of sharp edges can be challenging sometimes, but more importantly, the design of your part for that motor also can be challenging. If you look at the Prius motors, you will see that they make a magnet, and at the end, in the slot, they have a little small notch. Each one of these variations, whether they're talking about the V shape, the bar on the top, the curvature at the bottom, they have implications on your speed of simulation. It can also have an impact on the cost, because tooling costs can go up. If you're trying to get a shape that is very unique, you want to create a fin shape, that's going to be challenging. You might have to do a mold, right? So that itself, so you're correct in terms of the shape, rounding off of the edges. Now, in terms of the teeth of the stator or the rotor itself, that depends on the design. I haven't done the smoothing of the edge directly, but that's an impressive improvement. Anything else that comes to mind? Right.
How the flux distribution is there, and we try to make the barrier following those flex lines in order to achieve high safety.
So that's fantastic. So did you do that manually, or was it an automated process? Okay, so I mean, once again, this is just my thought. If you're talking about something like that in which you're trying to optimize the design, you definitely have the option of parameterizing, right? You can go into ANSYS, you can parameterize it. You can decide specifically, not for the shape itself, but you can parameterize different lengths. It will create multiple geometries for you across. We did parameterization using ANSYS, but sometimes you do have to, in our case, what we found out was that analytical methods gave us more flexibility. So one of the things we're doing with this kernel-free method is actually a very similar approach. And I talk about that very much later, in which we look at different methods for optimization. And you're right. To start with the rotor core and start chipping away at the unnecessary parts, it's a very interesting idea. It makes perfect sense. It's not as easy as one would think it is, which is why you're getting a PhD out of it. But the idea itself is very practical. If you don't have that material to be useful, you can eliminate that, because you are not only trying to use flux manipulators to shape your magnetic field, you're also trying to lower your weight. When you lower your weight, you actually end up getting a much better power density, much better energy density, which in today's day and age is very important for unique applications like hybrid vehicles, traction drives. Any other thoughts or comments before we close out for this first session?
For that, only that point.
Yeah.
We have seen the motor of BMW 3i,
Mhm.
and at the corner of the rotor, there are only tiny parts where the flux can flow.
Mhm.
It might cause the saturation at that point if we reduce that material too much from the rotor.
Correct. As that bridge that you have, they do that. They put that bridge for structural support, because they wanted to make sure it does not have too much of a structural deformation. But you're right, you will create a hotspot. Now, once again, the question is, how bad is the hotspot and what consequences? How much heat does it end up generating? Is definitely so. To your point about what you're doing with FEA, that's one of the main places where FEA has a significant role. Analytical methods might not give you the calculation of that local hotspot. So you have to have a method that if you're designing something, either you have to go FEA or you have to go much deeper into applied math. The method we are using, like I said, the kernel-free method, our approach is to look at everything like fluids. So basically, just like a fluid flows, your boundary moves. There are no sharp edges. Water never goes in a triangle, right? Water always flows in a continuous boundary and it spreads. So if you think about it, whether you're talking about heat, noise, they have a similar boundary that actually spreads across heat and everything else. They have a similar movement. So the idea of exploring how it is going to flow if you put something along the way. We do the same thing with magnetic fields. If we want to actually do something, we're trying to eliminate a field from going, we put a negative polarity next to it, and the flux, we do that in real life, right? So the idea itself is very effective. You are correct. And this area is very rich. A lot of work is happening, but there's still a ton of work to be done. So let's do this. Let's take a quick 10-minute break at this point, and we'll come back in 10 minutes just to kind of stay on course. At 11, a little after 11:15, we'll go ahead and take off for round 2. Thank you. Check, check. Do you have any way of knowing? Check, check, check. Check, check. All right. Welcome back, everybody. Thank you for coming back for session 2 of day 2. So might not be the battery, maybe it's connected. Good. I can use the keyboard. Keyboard works. The arrow keys, yeah. Or not. I think maybe when you went from Zoom, because last time also started working when we went out and came back in. If it's not working the keyboard, I can. And then go to control. Yeah. Now go to control L from there. Oops. There you go. It's good. Better press a little harder.
Yeah, a little harder.
Okay. Okay. All right. So now let's start talking about mechanical design. I know at this point right now we get to a place where for some of you guys it's useful. For some of you it's a little more than you had thought you'd be doing in this class, in this short course. It's not a class, it's a short course. So mechanical design of traction motors. This is one of those topics where if you're talking about it as an electrical engineer, oftentimes we have always assumed that there'll be somebody else who takes care of it, right? There's a mechanical engineer who's going to come and design the machine. However, when you start looking at the overall system as a function of interdependent variables, you need to start planning for the mechanical design. So what does that mean? When you talk about mechanical design, a lot of the information, by the way, in this in the next couple of slide decks are going to be more word heavy, not as many pictures, but more word heavy, because I wanted to make sure the context is clear. In previous cases, I knew that if I said it, most of you would absorb it. But with the electrical engineering heavy room, I wanted to make sure text was available for you to take a look at it as we go forward. So the design of electric motors really starts off with the basic idea of the design requirements. Like I said before, if you see me talk about this a lot, we will start talking about the 2025 design targets a lot. Why? Because if you don't know what you're trying to design for, it is very difficult to come up with a method. A method does not work in isolation. A method has to work in the context of a given application. So electric motors basically go from design requirements to operating conditions, material selection, integration, bearings. This forms the overall layout of the process of a motor design. If you take this further and break it down into machine design, you will look at the actual structural design of the machine starts from concepts of fatigue, stress, torsion, manufacturing tolerance, fitness, bearing, material, and mechanical losses. So it's not a one size fits all where you say that what I'm going to do is I'm going to make sure my bearing is the best. I'm not going to use ball bearings. I'm going to use, it's going to be a bearing-less machine. I'm going to have magnetically suspended whatnot, and I'm going to have pneumatic bearings. Whatever you decide, you say, I've solved it. No, you can also have things like a fatigue crack that forms as well. You can have epoxies that actually start to deteriorate over time. You can have insulation that has breakdown because it was exposed to a lot of heat over the course of time. So what this means is that your process really starts to look a little more detailed than you have thought. Starting with customer specification to type and topology, you always start off with the basic idea of preliminary design. That takes you into a dimensional sizing. You have to have a starting point. You need to know what your constraints are because that came from the customer or your specs for your application. That gives you the initial dimension. We did that calculation yesterday talking about the torque and speed requirements and the power requirements. From that, you start to go to the process of optimization, and you go all the way to testing, only to iterate. Now, you can actually add one more variable where you can actually go from machine design to optimization and close the loop back with machine design, because you would create multiple iterations of any design before you finalize on your simulation itself. So in the material design, in the mechanical design, you have a few key variables that you need to remember about. The first one is fatigue analysis. Fatigue analysis is the cyclic loads that cause microscopic cracks. That can lead consequently to significant material failures. You can even have things like, if you're talking about the laminations where they separate, right? I don't know if you have seen in motors, sometimes it can get to a place where they separate, in which case all of a sudden your field distribution is not as uniform as your original design was. It can also happen, fatigue can also happen at stress levels where your tensile strength or yield strength is actually exceeded. And you can have options where, or scenarios in which you have an alternate load that you had not planned for that happened. Let's say you have something as simple as changing the atmospheric conditions, where now all of a sudden what you had designed it for didn't account for the fact that you are at a different level of pressure, at a different temperature. Same things as what you might imagine for something like photovoltaics, right? You have to think about where is it going to end up. If you don't do that, that can create an extra load that was not planned in your original design. And the second one is mechanical stress strain. That basically is the method that allows you to determine the ability to withstand different loads. It also has planned for failure rate. So you have to look at MTBF, mean time between failure. How often or how regularly can a failure happen? Oftentimes you use methods like 3D analysis, 3D FEA for defining the stress analysis. Then you have to look at torsion. Torsion basically looks at the motor and the load system, and it identifies the inertia that is going to be applied. Buckling analysis is essentially the compressive stress that you get in your system, and that can lead to a loss of stability. For example, oftentimes we talked about this as well a little while back. You might have an I-beam or a pi beam that actually is used as the ventilation duct in your lamination core. You are doing that in some cases to add structural stability. You might be doing that for heat or for heat extraction or for maintaining the shape. They might be used as spacers. And if you do analysis, you can make sure that what you're doing is not going to cause a hotspot. It's not going to cause a failure, and not negates, but actually kind of undermines the reason why you put them there to begin with. And then, of course, the manufacturing processes. We will talk about manufacturing processes later as to what they are and how they operate. You need to be looking at the idea that if you are using a method that is cost effective, is there a trade-off? Are you looking at part geometry? Are you specifically considering vibration and dampness, surface finishing, basically whether it is enclosed or not? Once again, where are you actually deploying this system? So, for example, you need to figure out also what the process is going to be. Let's say you want to do a die casting. We will talk about die casting very briefly, what that is and what that looks like. So you do need to figure out what your manufacturing process is. They all have a trade-off that specifically has an impact on the overall deployment. So when you're talking about mechanical design, you have a few steps you need to follow. Or a few checkpoints you need to consider. The first one is GD&T. That's geometric dimension and tolerance. Not only do you need to know what the design for each of your parts is, if you have ever sent your laminations for manufacturing, they will always ask you what the tolerance level they can allow, or what you allow them in terms of the tolerance, right? You also need to have repeatability and streamlined assembly. If you don't do that, then taking it to commercial production will create major problems. We have to design a system that is not meant to be so high or so strict in its tolerances that manufacturing requires very specialized equipment. That will increase the cost. You have to have a fitness between a mechanical mating component. So if you have a male and a female component, you have to make sure you have lower vibration, that they actually have good coupling. You have torque couplers we talked about. We have the rotor that is fitted inside a hub of a wheel. We have to make sure those tolerances are designed very carefully. If not, if you have a coupling that has basically has a wiggle space, or give is what we call it. If you have a little bit of a slack on it, you will end up creating a slapping action. That will, over time, is just like having what water does to rocks, right? Over time, it will erode, and that vibration will continuously keep getting worse. Then, of course, you have bearings. You talk about this a lot. We talk about this a lot in different applications. Bearings are actually one of the most important components in the entire design, in the mechanical design. You have to make sure you have the right grease selection. You cannot just pick a ball bearing because you want it to. Then you have materials for motor components, where you talk about reliability, manufacturing process, and oftentimes all this is a function of how long you want the system to operate. Because if you want it to run for 15, 20 years, you have to make proper selections where they have a basically they maintain their property, they retain their property for that period of time. In terms of losses, we talked about losses just a few minutes back, mechanical and electromagnetic power loss along with electrical. We have to define the right material for the wires and the laminations. You have to account for losses in friction and windage. You have to look at CFD for specifically for giving you thermal behavior analysis, because that heat causes secondary losses, secondary effects, right? If you have heat loss, it will actually cause your degradation in every single subsystem that goes forward from there. And of course, you have to look at eddy currents and hysteresis loss. So if you look at the mechanical design itself, the comparison, if you look at the failure modes of mechanical design, this is actually I wanted to just make sure I was getting right. This was information that there's a very good book on mechanical design of electric motors that specifically looked at a case study with 1,141 motors, and they were larger than 200 horsepower. So these are all typically large motors that specifically they were looking at, and they published data. This basically is a data that came from IEEE and another one that was done by EPRI. So two agencies, two groups did a very similar analysis looking specifically at the failure contribution. And what they found out was that they had a somewhat similar in terms of behavior. So what you see here in the table is that your most common reasons for failures that basically happen because of stator insulation. That is really one of your primary reasons. So I think we had a conversation at the very beginning. If you're talking about losses that happen in the stator, that's one of the reasons why we are so particular about how we design it. So we can also have, if you have higher vibration, you can also end up with creating a lot more mechanical failures. And of course, your failures are related directly and indirectly to the operational temperature. So if you look at, so the same thing, basically just continuing the table here as well. So in terms of mechanical losses, you will see percentage of losses that you get for mechanical total losses is at about 30%, which means your system is very prone. So we think constantly, whenever we're designing an electric motor as electrical engineers, we often think about electrical design. We talk about electromagnetic design, right? We don't always think about how we are going to design the overall system. Sometimes you can find out the hard way that if you start the design without knowing how thick your housing is going to be, you might end up with a motor that doesn't fit your desired application, because they have volumetric constraints, they have geometrical constraints. If you design a motor that is bigger than what they want or what they need, it won't fit. If it's too small, you might not have the right amount of power. As a result, you need to make sure there is an actual structural analysis that is happening as you are designing the electric motor. So it cannot be an afterthought at the end of the entire idea. That leads us to the next important issue that oftentimes gets ignored: standards. How many of you guys have actually at any point come across standards, whether it is in a class, in a course, whether it is in a research or in a project? Has anybody here had to deal with standards? For automotive, for drivetrains and everything, mechanical standards oftentimes on the automotive side would be in SA. You're right. Anybody else? Exactly. You have electrical standards that are defined specifically for applications, especially if you're talking about grid type systems and all that kind of stuff. Standards exist for a very good reason, right? The goal really for standards, for example, we are currently working with Underwriters Lab. So they actually have one of their offices not too far from us in Chicago. And we are working with them specifically in the area of fast charging of batteries. The reason I have a substantial respect for the work they do is not just because we work with them, but mostly because the job that they do is largely underappreciated. If you flip your device, any charger that you have, a laptop charger, anything, you'll always see a certification in the back, right? You are designing the system such that it incorporates certain key requirements of the user to the manufacturer. So one of the key jobs that the standards developers do is they survey the stakeholders to find out what are the most important components. Then they look at the integrators. They also look at the end application that is deployed. Using that information, they define specific standards that the companies or the manufacturers have to follow. If you don't do that, you end up in a scenario in which your motor sends out EMI and could disrupt somebody's pacemaker, for example. You might end up with acoustic noise that causes somebody's hearing aid to start making very loud and very unbearable noises, right? So sometimes you have to look specifically at what you're doing, because what we are doing is high frequency switching, right? We are causing a very high voltage to collapse very quickly by switching back and forth. When you increase the frequencies, that EMI radiation is going to be substantially higher. So you need to make sure you are accounting for that in your design, and that's what standards specifically test. So you have to take your finished product, get it certified for standards. They will do sample testing, or they might actually do every single unit that you send out, and based on that, they will define whether or not you have passed the standard. So they give you a specification that basically, so they make sure that there is no specification that can be misinterpreted. And that means that every competitive product, so let's say you're talking about, I'm not going to use Apple and Samsung because that's a different ballgame altogether. Let's say you're talking about a wireless charger of some sort, or a charging pad, and you want to launch your new charging pad on the system. One of the devices I brought with me is a bottle that has basically a ultraviolet light that it's a smart bottle. Basically, it sanitizes your water. And somebody gave it to me. That's not necessarily my thing, but they gave it to me. And one of the patents that they have is not in the bottle, not in how they clean it. I believe their patent actually is in how they charge the cap. It's the bottle, and then you put the cap on top, and it's a arguably contactless charging, because it's still going to sit on top, but it is a contactless charging. Now, those kind of charging systems, if you are designing something that's not going to be used everywhere, not everybody is going to buy it, you want to make sure when somebody is charging their bottle, they're not going to get electrocuted because you have water right below where you're charging it, right? So you have to have certain standards. As a consumer, you have an expectation of knowing that if I'm putting my motor in the rain, is it or is it not going to get damaged, right? That brings you to the question of enclosures. We will talk about enclosures, because you have to know not every motor works everywhere, right? I mean, if you have made mistakes of that, including light bulbs, you place what's supposed to be inside the house, you put them outside, you will find out very quickly they don't last nearly as long as they should. So there are multiple standards for motors. Oftentimes we look at NEMA standards. We also look at IEC as well, that is International Electrotechnical Commission. And for us in North America, NEMA standards is really what we go with. So there's also the IPC, which basically is IP code, which is very different from what you guys call IPC here. But it is basically specifically for electric devices. So the code really, when you look at the IP codes, you're talking about 2 digits followed by 2 letters. The digits are required, the letters are optional. The digits basically give you, and there's a whole table of what each digit represents. And I just picked a couple of them because they were things we probably relate to. For example, the first digit, if you have 2, it is protected against contact with fingers. It is important to figure out how or how not things can happen. I mean, I'm sure you have seen it as well in terms of lawsuits. There is malpractice. There are intentional and unintentional consequences of what you did or did not plan for, right? If somebody figured out that you designed this to be used outside, but the first chance it rained, and then it got hot, it explodes. You have a problem. If cars are catching fire when they're sitting outside because there's a BMS issue, once again, you have a problem. But in this case, this is for motors specifically. So the first digit gives you protection against fingers, for example. The second digit, it basically has protection against direct sprays of water at a 60-degree angle. There's another one, I believe the second digit being 2 is protection against water at 30-degree angle. You might wonder why it is important, because you are actually accounting for how much rain, what kind of water flow, what angle the water could be coming in for you to be considered to be basically outdoor safe, right? So this IP23, if you combine 2 and 3, gives you a weather protected motor. So those kind of requirements dictate how much active space you have for your motor to be designed. If you don't select the right value, you will end up, if you don't select the right housing, you will end up with insufficient space for your motor design, which will then cause a lot of secondary issues, right? The letters basically are against hazardous parts, and the second one is also have letters with hazardous parts. So you can have basically A and H, back of hand, and high voltage. So if it was written as IP23AH, you would say that it's protected against contact with fingers, outdoor weatherproof. It is protected from back of the hand for hazardous parts, and it's protected from high voltage devices for your hand. So that would be the combination. That's the certification you are going for. What defines it? Your application. You decide where you're going to launch it, and you decide what kind of a code you're going to get. Class H, for example, is very typical. If you want to go for high voltage designs for HVAC applications, traction, you might be looking at Class H motor. That is very typical for you to consider. So the motor housing, like I said, it has three primary functions. It's very intuitive. It protects, it cools, and it's used for mounting, right? These three things always happen, which means you need to make sure how can anything enter the housing. You have to decide how is heat going to exit, and how are you going to mount this unit to your solution. Is it going to be a face mount? Is it going to be a foot mount, right? In some cases, you might, in a very odd scenario, I would imagine it's possible we have a suspended system. I haven't come across one, but arguably that's possible. And then you have a housing requirements of, are you going to mount the magnets directly into the housing? That's also done, right? Traction motors do have that. You're trying to save space. You can, if you're using something like Alnico magnet motors, in that case, in scenarios like this, special cases, you might have the housing that is made specifically from non-magnetic materials, which you can use aluminum, brass, stainless steel, and such. So in terms of the manufacturing of the housing, you can do it multiple ways. You can either have a housing in which you wrap the housing around the motor. That basically means you wrap it around the motor, and at the end you weld it. You can have a casted housing, which is oftentimes you actually will see that was a very popular method of doing this, in which you have a phase change of the casting material, where it basically goes from its liquid molten form to a solid form. So you cast it. It is very useful for applications where you have a mold that you have designed specifically for the application. It doesn't make sense if you're doing a prototype. For a prototype, you might find much more expensive, but much faster ways of doing this, because this has a tooling cost associated with it. So cast iron oftentimes will be iron carbon silicon housing are typically used for heavy duty applications for large size motors. Next, you have mechanical stamped housing and extruded aluminum motor housing. Why are these important? Every one of them has a very significant role, like I said. If you're talking about machine housing, it might be used for fast fabrication. You want to create a prototype? Great. But your manufacturing, the CAD design you have created needs to be compatible for your commercial deployment. You can do this as a process, but the tolerances should be compatible with the overall end application you are going to select. Stamped housing as well, you have metal sheets that you can actually create into specific shapes, and that allows you to create small size, large volume ordinary motors. We don't use them, for example, for traction motors. They are more used for smaller motors. And of course, extruded aluminum housing, in which you can create several complex shapes. Now, if you talk about materials, if you're using something like composite materials, by definition, it's going to be a little expensive, but it gives you reduced weight. You can have lowered vibration transmission. Why is this important? It is important because if you have an application, let's say aerospace, naval applications, DoD kind of stuff right now, where you want to make sure that none of this is actually transferred. In that case, you might have the option of looking specifically at composite materials that they can have resistance to corrosion for ambient conditions. You're deploying it in a place where you're going to have a lot of dust, offshore wind, for example. You might be looking at a boat application where you're going to have a lot of saltwater spray happening. Corrosion can be a very big problem. In cases like that, you might have something like this be relevant. 3D printed housing, it's something that I know we're talking about 3D printed everything these days. So it definitely converts it into physical objects very quickly. It can be expensive, especially if you're 3D printing metal. Metal fab can be very expensive, however, or at least the machining that you have to get can be expensive, but it's a very good way to do it if you have the right equipment. The last one, of course, is the frame design. Get rid of the entire frame. All you have is the motor, but that means you're going to mount your machine directly onto, let's say, a transmission system, right? So in cases like that, you might be looking at airplanes, satellites, where space is very essential and very important commodity. So if we move one step further in the in the structural design, you now go into the space of winding. So we are going from outside in. The only part I won't cover right now is going to be the shaft design. There is actually a very good paper specifically on shaft design. You can look it up. But because of the timing that we have available, I'm trying to stay just with the active material and not going directly into the shaft design. Which, by the way, is very important, because if you have bowing, bending on the shaft, that's a whole other kind of problem, because that will lead to other secondary issues. So I'm not undermining the importance. I'm just saying we will not have enough time to cover that. So stator winding really has, we know copper has better conductivity than aluminum, right? That's a well-known fact. However, copper can be more expensive. You also have to source copper. Aluminum is abundant in terms of bauxite, which is basically the ore that we use. It is very easily available. And if you want to go expensive, silver is better than anything else. But then again, it's silver. I mean, we use silver in sparing quantities just because it is not easy to get and it's extremely expensive to manufacture. It also gets tarnished, by the way. If you remember that I mean, if you've seen, I'm sure some of you guys have at some point polished silver for somebody in your family at some point or the other. If you haven't, well, in that case, you were not pushed far enough. So, but it's not suitable for motors as much. So I was just joking. Please don't take me wrong. It had nothing to do with anything. But the idea really is silver does get tarnished. And that's the fact you have to remember. We polish silver for a specific reason. Brass is polished for a very specific reason, right? So that means for electric motors, where you are going to expose it to different conditions, that might not be the best solution, especially if it's going to get hot. But it's a good conductor. So that basically means you can also have a second option for magnet wire. Magnet wire really is a copper wire that is coated with enamel. Yesterday, I think we had some of you guys who had questions specifically about what those wires are and what they do, where enamels and epoxies would make their way. So in terms of if you're coating them with enamels, you can actually have them sit adjacent to each other. Why is that important? When they're adjacent to each other and you don't have to have a thick insulation, you end up getting much better fill factor. Fill factor really is a function of how much heat you can basically, or how much voltage you can handle, what separation you have to have, what dielectric you need, right? So that you don't end up having arcs that creates a short. So you can actually have, in terms of small and medium motors, you can have regular magnet wires, you can have self-adhesive magnet wire, or you can have Litz wire. So if you look at the specific design of the way these three specific wires are done, the regular magnet wire has a base metal. It usually is going to be copper aluminum and is coated with a single or multiple layers of insulation. That layers, the number of layers you're selecting is a function of what separation and what voltage you are going to apply specifically to your motor. You can also have designs, and that's something that's been extensively been looked at in terms of a trade-off between cost and design complexity. You can go for a round, you can go for square, or you can go for rectangular winding. Oftentimes you will see people talking about doing rectangular winding because square by definition leaves out space, right? So which means you have gaps in between your wires that are bunched together. Square or rectangular, on the other hand, can actually sit next to each other and give you much better fill factor. You have to remember that what we had just a comment a little while back, if your slot is curved at the end, that means now you're going to end up with a square shape that might have a difficult time fitting into your slot. So it's always a design trade-off. You have to figure out what design you're going to get, but you are always trying to go for the highest fill factor because it gets you the most amount of current, with the exception of what? You want to get the most amount of copper as long as, what's that constraint that's going to hold you back or that's going to not let you go too far with it? As long as, we talked about this a little while as well. What are we trying to make sure the windings never get? Heat. So the question really is, how hot are you going to get? When you put more copper into it, the question is your thermal behavior, thermal system robust enough to extract the heat? If you're trying to do forced convection with air flowing through it, and you have a packed winding slot or a slot with winding in it, it's a problem, right? On the other hand, if you have something that actually extracts the heat, like a heat pipe, or you have epoxy or something that allows you to extract the heat directly, now you have the ability, like potting, for example, allow you to extract the heat, take it to the lamination and outside into the fins. The self-adhesive wire basically is a thermoplastic adhesive with superimposed standard film insulation, And Litz wire, which is one that currently, like I said, a lot of people are looking specifically at the Litz wire very carefully, is because it has multiple strands. They're much thinner. They're capable of withstanding or basically not having to deal with too much of eddy current problems, and they're twisted together. So that also allows you to have a lot less interference between the windings. So when you talk about the winding, the next layer you are thinking about in the machine design process is how are you going to design the machine? What you don't want to do, you don't want to stick the windings in there and not think about whether or not you're going to have a short, right? So the first step that most of us might have seen at some point is a slot liner. It's basically is a liner like a butter paper kind of thing that's sitting in between your winding and your lamination to make sure we don't have a short circuit. So it is inexpensive material, but because you're basically putting in slot liners individually into the slots, it can be an expensive and a drawn out process. It depends on how much is available. The next one is basically injection molded plastic insulation. It is reliable. It works it can be an automated process, and you can actually have consistent thickness because you are directly injecting this into your motor. You can have glass fiber reinforced mica tape. This is typically done for large motors that are in the range of kilovolts, high voltage designs. You can have tape. So basically the idea is you design the whole thing and you insert it, right? So you're basically creating a nice formed coil. You get the maximum basically compactness into it. It is wound around with mica tape and you put it in. So that's one way to do it. You basically and then you impregnate that, and that basically allows your insulation to be cured, and that keeps the entire thing secure. You can also use this as a way to make sure your windings don't vibrate inside the housing, because that could be another source of noise. And the last one is powder coating on the stator core. This actually is typically used for insulation material for powder coating, epoxy, Gliptol, and Loctite. These are materials that you can actually spray on the winding to allow you to have a protective finish on your electrical components. In terms of what ways you can use for winding the stators, you can have hand wound, distributed, concentrated, or conductor bars. Conductor bars are something that everybody would like to have. It is a little more drawn out process, obviously, because you are trying to create a conductor bar that's prefabricated. You have that tape around it and you insert that. Concentrated coils, has anybody here dealt with a concentrated coil, or do you typically, in most cases, most of the applications, have you always had distributed? Anybody here who've used concentrated coil before? So if you have done any work on switch reluctance machines, you will see concentrated coils be used quite a bit, right? Because they are individual phases. Each pole has a coil wound around it. There are real benefits. If one coil goes out, the other coils are not affected. So that's a real benefit. However, there are also challenges because your copper volume is lower, which means you can actually end up with somewhat lower power loss. All right, so because you are putting adjacent coils next to each other in each slot has two sets of windings going into it, which can directly have an impact on how much copper you're able to fill because there is some spacing that creates. It can also have a higher induced EMF and you can have more harmonics. On the other hand, distributed windings typically are done for creating that sinusoidal waveform. You're trying to eliminate harmonics, trying to get the best behavior for your motor, electrically speaking. If you take it one step further, you've designed a machine. Now you had to think about what affects your overall motor performance. The first three things basically is phase voltage imbalance. We know what that means. We're talking about imbalance that happens in the fourth generation because you have a three-phase system where VA plus VB plus VC, not zero. If you have a phase imbalance, it could be between because of shorts between two windings, two coils, or phase to ground, or any of those combinations. Even if you have a small negative sequence, you can have currents that actually cause significant amount of damage, right? You can also have bearing currents that actually happen as well. I don't know how many of you have seen it, but bearing currents can be a very significant cause for bearing failure because you have currents because of anything that is malfunctioning within the motor can cause your bearings to carry current. And in addition to the current being felt by the user, it also causes the lubricant inside the bearing to dry up, and it can actually cause failure in the bearings itself. So that is something that you always have to consider when you are talking specifically about the voltages you have. Just for example, if you have a 5% voltage imbalance, you can have a 30 to 50% increase in the current imbalance, and that goes with a 50% increase in the motor temperature. So the numbers are very staggering in terms of what you could see. Now, arguably, if you're within a tolerance, you're still fine. So there is a trade-off as well between robustness and your design requirements. right? So we actually have, I have a table that from my notes that I did not pull out. But in terms of terminal voltage, when you're talking about the full load, you typically your efficiency does not vary very greatly when it comes to terminal voltage. But when you're talking specifically about the current, that has a significant impact in terms of losses. We have iron or core losses, we talked about that. And if you have a sudden change in the applied load, you might actually stall if your voltage is not right. We've all seen that, right? I mean, like I said, simple applications like a blender in your house. You turn the blender on, you put ice or you put some vegetable or some fruit in it, and it just wouldn't blend, it just wouldn't spin. It is a function of how much power you're able to generate. And if it has enough voltage, it will try to generate more current. At some point, it will start to drop the voltage level. And we've seen that as well. If you have ever used a hairdryer or a heater, when you have a light on, you will see that voltage dim. That's the voltage drop or the voltage sag you're going to experience. So you really do need to think about, in our case, 60 hertz, in your case, 50 hertz. You need to look at specific losses that you can have in terms of your system. And of course, the last components are harmonic distortion. If you have done power systems even a little bit, you might have looked at these concepts, the idea of harmonic distortion, voltage flicker. These are very important components that are very present when it comes to electric motors. You don't want to have, a flicker basically is just like the name says, it's a small, short duration burst of voltage that you can get. But the DVDT can have an effect. For those of you who have worked on converters or motors, you might have noticed if you have a sudden spike when you turn on or off your switch, what happens? It either will trip your breaker if you're designing a motor, or worse, it'll burn something, right? I mean, so your DVDT, so what do you do if you have high DVDT? There you go. You put a snubber circuit, right? The idea for dealing with the DVDT is putting in RC or an RCD snubber. That's the go-to. So that's a real thing. So when you're talking about motor windings, you do have to take into consideration. Whenever you're designing a machine, in addition to all this, just keep in mind, you also have to account for the wire, the cable that goes either from the inverter to the motor or from the supply. Because that inductance and the resistance that has to be accounted for in your controller. Because you have the length of your conductor, certain amount of R, but the length of the wire that goes with it has a contribution to play in what your drop in your winding is going to be. If you don't do that, once again, your controller algorithm is assuming a certain resistance. If you don't take into consideration the length of the wire, and let's say hypothetically it is relatively long, first and foremost, you will have a variation in your resistance. Option two, if you create a loop, you create a what? If you have a loop of conductor carrying current or voltage, what do you get? Actually, no, if you have a wire that runs in a loop, in PCB design, that's one of those things you always talk about. You don't want to have big loops when you're designing a PCB because it creates what? Yagi-Uda. Stray, but yeah, but Yagi-Uda, you guys are on your rooftop. It's an antenna. Basically, it radiates. So that's the basic definition. That's what your rabbit ears and everything have, those loops, right? Because that's the mechanism we use. So if you create a loop and you create something like that with your wire, you need to consider what that's going to do to your EMI. So yes, so stray inductance or EMI would be a consequence. So a lot of times, currently what we are looking at is an IMD, an integrated motor drive, where your controller sits inside the motor. That is by definition very effective because the connection points are exactly what you have within your motor. Whatever is external to the motor at that point has no relevance because you have designed the controller to have accurate information about the length of the conductor from the converter to your winding. And now your controller is more accurate. Absolutely. You are correct. So yes, so it is something you have to take into consideration. So if you are going to have something that's very power dense, there is some work happening. If you look at the work done by NASA in particular, they do a lot of work in that space, and with IMDs, they had some projects also that they sent out, and they were looking specifically at IMDs. IMDs actually is something that Professor Tom Johns from University of Wisconsin at Madison, he has done quite a bit of work in the area of IMDs, and they've published quite a bit as well that you can definitely take a look at it. And I believe their project was actually a NASA project. So if I'm not wrong, it's a 1 megawatt motor, if I'm not wrong, but don't quote me on that power level. But the idea, you're right. If you're putting it inside, that's really has always been the constraint. There's a couple of things. First, you had to figure out how big your circuit can be. Because if you're talking about SMDs, great, but you still have to go smaller than that, right? You have to change the packaging so that you can have more components. And then you had to look at how much noise you're going to radiate and how susceptible to EMI that converter is. Because remember, electromagnetic fields are susceptible to the distance. If you keep it very close, all the noise in one system crosses over to the other system, which means now you have solved one problem, but you have to answer another. I'm not saying you have created another one, but you've definitely gotten a lot closer to another one. So one in temperature, of course, you're talking about the life cycle of the insulation. The 10-degree rise of reducing the insulation life in half is basically, I believe it's called Arrhenius equation. And Arrhenius equation basically is an equation that goes with the chemical behavior, which also applies here. Because we're talking about the flow of electrons, it actually specifically deals with the fact that if you have a 10-degree increase in your temperature, insulation life is cut in half. If you reduce the temperature by 10 degrees, you also cut down the, you also increase the life of your insulation. So your temperature of operation has very direct relevance to how long your electrical system is going to be intact. So that is something you do have to work through. So this is basically your cooler experiments, cooler setups would have much lower losses. So for example, if you have a 10-degree reduction in temperature, you will have a DC resistance loss on the conductor by 3 to 4%. You will reduce the DC resistance. That directly leads I square R. If you're talking about 150 amps, that's a very substantial change that you're going to see. So in terms of core lamination, I'm going to get done here. So in terms of core laminations, you have to look at the approaches for how you are designing the core. The selection of the stator core material. You don't have any centrifugal forces on the stator, which means you have less of a concern about mechanical forces, right? But you have to look at whether it's fully processed steel or annealed steel. Annealed steel is very typical in our applications in North America. They are high performing electrical properties, they're fully processed, but depending on the fabrication capabilities, you would use that. So fully processed steel usually has silicon in it that allows you to have an insulated coating. It's not annealed, which basically means after punching, you can save some time in the process. This is the last really big topic that you need to think about when you're manufacturing an electric motor is stamping. How are you going to cut your lamination? If you do a stamping, you can imagine if when you stamp it, you're going to create an edge or a ridge on your lamination. It's easier. However, it also creates burrs or warps near the edge. Basically, just like anything else, when you punch it out, it was want to bend at the very end, which means your stacking factor, it might not sit as uniformly as you would like it to be. Laser cutting is a very nice option if you are doing a prototype. It's fantastic. It's expensive by definition, but it's very high accuracy. Electrical discharge machining is basically it's a negative removal process. It's a negative manufacturing process in which you remove extra content as opposed to adding anything else in it, and you apply bursts of current discharges that allows you to really chip away. It's like chipping away at your material. And of course, you can have CVD, chemical vapor deposition, or chemical etching that allows you to create specific design. If you want to have a pattern, let's say you want to have laminated steel with the right structure, but you want to deposit certain properties on it, you can do that. CVD is an emerging process. It hasn't been done to my knowledge in motors as much, but it is a topic of interest. So like I said, annealing is a process in which your residual stresses are introduced during cutting, and that can actually lead to a large amount of cogging torque. That's why it matters to us. So when we talk about structural, we always think about the fact that, well, it's structural. Design the motor, we'll do structural. No. The way you do your structural is going to affect the way you do electrical properties. It does have a direct feedback into our system. So if you're talking about a small stator size, in that case, a larger cut affected zone can have a very significant impact in how your motor behaves. It can have a very significant impact in how many laminations you can stack. So the stacking is basically what comes back. You have welding, bonding, riveting, or fastened by pins. The names are self-descriptory, right? They actually tell you how you're supposed to put them together. You can either weld them together. Make sure you're not welding the high field components. You created laminations for eddy currents. Don't weld them, because if you weld the parts that you laminated, you just created a path for it to close again. You can bond with adhesive material. You can create rivets that allow it to kind of lock into place, or you can have pins, but you don't have the problem of a bolt that goes with it. You can have lamination interlocking. You basically have locks that kind of sit in there. They sit next to each other. You can have self-cleating, slot liners, thin sleeves, or bolting. The reason I'm going through all of this is because if you don't think about these things, somebody else will. your motor design has to be an integrated process. And I'm working myself into this scenario in which we can talk specifically about this. This is my last slide. We know these because we talked about cogging torque. So that brings us to the idea of torque. We need to look at what we're designing for: locked torque, locked rotor torque, pull up torque, and breakdown torque. If you don't design them right, your motor is going to break. I mean, not exactly in those words, but it's going to have some damage to it. So here's my question. How do you balance the trade-off? I shouldn't even say have you. I would say, how do you balance the trade-off between all of these components? In your design process, what is the mechanism you think could be effective? You're talking about cost, life, application, energy cost, inflation cost, operational hours, maintenance cost, and loading profile. So there's a lot of variables from the structural side that we have to deal with. Do you have any thoughts on what you think is an effective mechanism? Don't feel pressured. If I don't want to put you in the spot, but if you have any thoughts, especially mechanical engineers or the WEs who've worked with teams, what do you guys think? Have you dealt with any of this stuff before for any application that you have worked on? If you haven't, then well, get ready, because you have to, like I said, the landscape of electric motor design has changed, is changing, and it's continuously evolving. The lines between when mechanical engineers could not do electrical engineering stuff is long gone. I know plenty of mechanical engineering people who do AI, who know about power electronics just as well, and they can get by without us. The same way, there are plenty of electrical engineers who know enough about mechanical engineering who can get by without mechanical engineering. We shouldn't, because it doesn't make sense, but it's possible. The point I'm trying to make is that it is important in the current scenario for an electrical engineer to have a very growing and active awareness of multi-physics behavior of electric machines. Without that, we end up creating a solution that might not pass muster, might not pass all the tests. So that really takes us over to the next topic here. I'm 5 minutes, within 5 minutes. So is the thermal design of electric traction motors and management. Okay, so can I just go into it? Are you guys still with me? Yeah. Yeah.
So, one of our friends said that there will be the thermal management issue. Related to vibration, how far vibration characteristics of motor influence the controller performance?
I haven't seen anything, so I have to be careful. I have not seen anything specific that I have found where vibration directly leads into it. I know harmonics. Basically, if you have harmonics that are created because the vibration in the motor that can couple with the circuits, in terms of direct impact on the circuit behavior, unless you are going to cause an insulation or cause a connection failure or something like that, I don't know what other impact there would be. And once again, I'm not saying there isn't. I'm just saying that I don't know of any other specific reasons. In terms of the components, you're not doing wire bonds anymore. You're actually doing PCBs. You're doing surface mount devices, right? So the way it's done, the wiring and everything is a lot more robust. So when you're designing the system to be within the motor, it has to take into account. But specifically for getting certified as vibration free or something like that, you will need to do a considerable amount of testing and do some life cycle testing specifically to see if there are any impacts. And there will be a percentage assigned to it, because you will find out that failures do happen on the field. So if you get a 7 to 8% chance of failure, that might be pretty high, and you might have to have some recalls. That's really where we end up. So unless we do full life cycle testing, accelerated testing, it is difficult to put a number on how each thing could couple back. At this time, I don't have an answer that I can give you about vibration. I haven't seen any numbers around that, so hope that helps some. Once again, back to us. Yeah, question.
The space between the stator and rotor, how it will be decided? It will be any digital value for all electric vehicles.
It's interesting you mentioned that. I think it's coming up later when I actually talk generally about the air gap sizes for each motor. There is always, oftentimes for the air gap design, there are rules of thumb, right? You have, if you talk about PM machines and such, between 0.5 to 1.5 millimeters. Switch reluctance machine, you'll be about a little less than 0.5 millimeters. So people have their expectation of what that number needs to be. Oftentimes, it is trained in terms of what kind of tolerance you're able to handle. For example, switch reluctance machines, if you want to have an air gap of 0.1 millimeters, that's very, very small, right? It's a very small gap that you're talking about. If you are at 0.1 millimeters, the question is, how do you manufacture it? You cannot laser cut it. Do you have to burn it away, or do you actually have to kind of shave it down specifically to give it? Is that reasonable amount of automation? So there are some general rules of thumbs that go around the tolerance, because depending on how much tolerance your stamping or your laser cutting allows you, that dictates what your maximum or the minimum air gap can be. In any scenario, you're trying to get the most amount of field that flows from a sedated rotor, because you want to have the least amount of losses. With EV traction, the added challenge is that you are also getting a lot of vibration from the shaft or from the mounting assembly itself, which if you don't have a high quality bearing going at, especially this is going at 10 to 15,000 RPM up to 18,000 RPM, at those speeds, you might end up with a scenario where you might have a clash between rotor and stator. So that's a secondary problem that is not unique, but it's definitely very particular when it comes to traction motors. So yes, there are some rules of thumb, but you would not see people defining it. In general, PMs tend to be 0.8 or above, up to about 1.5. But you will also see some cases in which they select up to 2 millimeters, we can have air gap. It's possible, especially if you have a high vibration environment, a slightly larger air gap makes sense. You might end up putting stronger magnets, which then leads to more cogging. So there's a whole cycle that you have to follow. I mean, there's a cause and effect for everything. Every decision you make has a cause and effect. So you'll have to work through your design trade-off to decide what it is that you end up going to do. That's a good question. So we talked about losses, right? I'm not going to go into losses again. So why do we need thermal design? Well, very simply put, high temperature gets to high copper resistance, gets to high losses. Simple as that. You cannot avoid your thermal design. It is going to get hot, right? The question is only that you're asking is how hot. Everybody's trying to get that efficiency of about 95%. Everybody's trying to get the power density. You want it to be quiet. You want it to be small. You want it to be efficient. And of course, at the end of the day, you want it to be cheap. Those don't work well together. They all have fundamental differences in each one of those objectives. So if you're doing a multi-objective optimization, your cost functions are going to be a little crazy, right? So you can also get non-uniform heat fluxes, and that basically is, like I said, is going to lead to what you call our Hea's equation. I'm trying to catch up. All right, so in terms of overheating, what can lead to issues of overheating inside an electric machine? You can have improper sizing or overload. We know that. You put too much power to it, it will start to overheat. It will try to draw more current. The more current it draws, I square R losses go up. Easy. Improper use, that's the one that oftentimes people don't take into consideration. You're not supposed to do certain things with it. For example, if you have a ceiling fan, you're not supposed to put your hand and see if you are able to stop it with your hands. As a general practice, and as a boy who was extremely curious, which is probably the reason why I became an engineer, is that we always want to see what happens when I do something, and does it break? And if it breaks, how much does it take before it breaks? That's that curiosity nature that we have in us. But it's a bad idea. Just objectively speaking, it's a bad idea, right? So in today's day and age, back in the day when the power levels were not very high, you could get away with a lot of things. In today's day and age, you can get to a place where, for example, if you go to a lab, or if you go to a traction drive test setup, which is actually operating at, let's say, 100 RPM, right? 100 RPM is not very high. It barely looks like it's spinning. It's going very, very slow. What you never want to do is you never want to put your wrist or hand and hold the shaft or the coupling, because those motors, if they're rated for, let's say, 2 to 3 kilowatts and at 100 RPM, they will take your wrist right with it. Because while it sees the extra load, it starts to crank up the current. As it increases the current, it will snap your wrist very easily. The point I'm trying to make is that improper use is something that people often tend to ignore or overlook. It's not always the case, but it's definitely something that you have to take into account as a manufacturer. Ventilation or ambient conditions, where are you going to be? Altitude change, like I said, if you're going to be at sea level versus on a hilltop, you need to plan for that. Overvoltage, the seal selection, current density, circulating current, harmonics. All of these issues cause heating. All of these issues are based on choices that an electrical designer is going to make. There are many ways to do this. LPTN, or lumped parameter thermal network model, is what appears to be simple. Actually, it's a very effective model. This is a relatively complex model. It looks very complex, and it is somewhat in some cases, depending on the level of granularity you want to create. This is specifically by Professor Boglietti, who submitted a paper, who had a paper on this topic. It is with TTE, no, sorry, Industrial Electronics, and you can see they actually have specifically talked about heat transfer equivalence. They talk about what it looks like for an electric motor. Your flow network that you have in the electrical circuit is going to be a function of converting pressure to voltage, volume flow rate to current, and flow resistance to electrical resistance. If we look back at what we talked about just a little while back, I told you that every system is trying to find its electrical equivalent, right? We're trying to convert mechanical energy into electrical, thermal energy into electrical, magnetic into electrical. So it is important for us to break down every loss mechanism, every behavior mechanism that you have in a motor, so that it can be represented adequately, so that they can talk to each other, which means you have to have coupled equations. Your electrical equation has to be coupled with the thermal behavior to create an outcome that loops back and tells and informs the system, if the temperature changes, here's how much resistance is going to change, which means our control algorithms have to take into consideration certain terminal measurements. You might only have voltage and current as terminal measurements, and that's good, but you had to start looking for signature that goes beyond what the harmonic or the THD is going to be, right? You had to start looking at, is there a fluctuation? Can I use a second differential, basically taking a second differential of the I, let's go d2i dt squared. Does that give me information? False isolation. You can look at all of those things specifically from the perspective of terminal measurements that are currently available. You can also use FEA and CFD, but LPTN can be much faster. The only challenge is that you are defining LPTN for a very specific geometry. If you want to have a method that allows you to change the geometry, you have to create a much more complex methodology. We are working on doing something like that for NVH design. As a matter of fact, right now we have some projects going on, but specifically we're looking at the idea of creating flexible solutions for noise, vibration, and harshness. The extension that we want to do also is for the thermal behavior. We want to do that to maximize, optimize thermal behavior. And I'll show you the framework within which later on today, I will show you the framework in which that is going to operate. So if you're trying to create an accurate model, it should be a model. It can actually be an accurate model can be challenging, in particular if you have a complex geometry. If you have a sharp edge, you have a fin, those things are difficult to model, right? Because your smooth surfaces are easy. You can define what the heat transfer coefficients are going to be. But when you start having very complex geometry, LPTN can have very significant limitations, which is when we have to go to things like CFD. So the CFD analysis of computational fluid dynamics is what we used. We actually did this for one of our race cars that we have built, and it's a very accurate method. It specifically allows you to determine heat transfer boundaries into the LPTN method and into FEA. It can tell you the fluid flow characteristics, and it can optimize your cooling methods, right? So the idea basically is what we were doing here was we were trying to look at the case study where we were seeing how much heat am I going to incur in my traction motor for my race car if I run coolant at a certain level. We were trying to figure out, do we need to have glycol, or can I just have water running through the system? What kind of coolants do I need to have? I think I have a number there somewhere. I had to go back and take a look at this. The maximum temperature I had here, I had to go back. The projects we're doing currently right now, we have seen temperatures, one of the projects we're doing, we have seen temperatures go up to almost 130 degrees Celsius. So we had one project, we did that. For this specific one, I think it was not taxed as much. It was a relatively larger motor with a bigger OD. The fill factor was not quite so tight. So I think this one did not go beyond 80 or 90 degrees C. So for water cool, it was more than plenty for what we were trying to accomplish. But I have to look back at the max temperature. I think I have a table somewhere. I don't know if I put that in here or not. I can always tell you offline what that number was. Mm-hmm. So in our case, the motor actually was designed. So what we were trying to optimize was not the fill factor. We were trying to optimize the cooling. So we had an existing motor, and we were trying to figure out how much power we can run for the given coolant. So we were trying to see, and the channels and everything, we modeled the channels out. to see what the coolant would need to be. We could not change the cooling loop either. The only thing we had control over was the flow rate and the material that is flowing through. That's all we could control. So in your case, like what you're talking about, you are correct. It would end up being something like a coupled model, which combines the thermal behavior with the electromagnetic behavior in the context of geometry. And I will actually show you a little bit later today as well that we did for NVH, like I said. So it's a little different in terms of shape geometry we looked at, but a similar option would be, I would imagine, would be effective. So analytical modeling. So this is kind of where we start going to the mathematical side, right? So we have three fundamental mechanisms for thermal modeling. You have you have conduction, we have convection, and you have radiation. We know all of this. We've seen these phrases and these terms be defined before. You are talking about conduction from surface to surface. You can have convection in which you are going through a fluid that is adjacent to it. So you have forced air, forced liquid, whatever it is that's flowing through it, or you have radiation. It just tosses it out into the ambient. You have specific equation that tell you analytical methods are always going to be faster, but they will have limits. If you are trying to do something very complex, let's say you are trying to even include something like nanoparticles or something, or to increase the conductivity of the coolant you're going through. I'm just putting it out there. I'm not saying that's what you should do. But if you do that, you might have a little more complicated coolant or heat transfer capability, because now you have some sort of a colloidal solution. It's not a clear liquid. It's not completely uniform fluid. So you would have to play through that a little better, in which case you might end up going to CFD, because that would be a much better way to analyze. So in terms of thermal design, need for thermal design in traction motors, traction applications, you are always looking for a much higher efficiency, right? You're talking about going to much high speed range. We want everything: high speed range, high torque range, high power, efficiency, low cost. I mean, we just everything in the kitchen sink, right? We want everything in the EV. So all of the optimization that you're talking about specifically has to have a mechanism that connects each one of these losses. You cannot just talk about one option and completely ignore the other. In some cases, with the switch reluctance machines, you will see that NVH radial forces are major. So that might be a primary objective function that you're trying to minimize. But you cannot ignore thermal behavior. So you have to start coupling them together in an overarching system, which, if you think about it, that's what software like ANSYS, JMAG, you name it, MotorSolve, all of them, that's what they do, right? They're trying to, what used to be only FEA, for example, in Politica, was only FEA for electromagnetic. Now they have combined with Mentor Graphics, and they combine the thermal behavior. Very recently, the company called PowerSim, PSIM, they got acquired by Altair. Altair also bought out Flux, right? So Flux is their solution. Currently, PSIM was using all of the integration with JMAG, but now they're integrating. I think I don't know if they're going to keep JMAG or not. I don't know that. That's PowerSys. But Altair is also coupling with Flux 2D and 3D, because they also have mechanical solutions. So right now, every solution simulation package is trying to recognize the fact that you want to see the circuit behavior at the same time as you see the machine behavior. You're not designing the machine and then designing the control. You are designing the machine as you design the control, rather the other way around. You design the control as you design the machine, right? So that's becoming your, it's a complex framework that you're trying to use. So in terms of the motor design itself, I think I had a question a little while back in terms of no, never mind. So there's a couple of papers that I think were relevant here. You can see these papers for hybrid cooling, for motor cooling system design. If you look at just in general for a totally enclosed motor design, it's about 1.5 to 5 amps per millimeter square. That's what tells you what your fill factor needs to be. How many amps per millimeter square? So it's not exactly answering a question, but you have a number that you can play with. That's a pretty wide range. I fully recognize that. Fan cool is between 5 and 10. Liquid cool is between 10 and 30. The range starts getting bigger and bigger as you go forward, because the options you have depends on what liquid you're using. It depends on how fast your speed is. What is the CFM, right? I mean, like, how many cubic feet per minute are you actually pushing through that motor? You have to dictate all of those terms in order to come up with a better number. For a given design, CFD can give you that answer, but you have to have a mechanism that allows you to model it properly. So this basically is just giving you a general idea of different cooling approaches. You have surface to air with the fan coupled. You have liquid cooling with the coolant jacket. You have a heat pipe with attached fins. And you have, heat pipe with attached fins. And then you have a hybrid cooling pipe with liquid. So you can see the channels. that are flowing through the outside. So it's basically an external cooling jacket. That's what we call it. It's a cooling jacket. The benefit of a cooling jacket really is it is independent of the motor design. You design the motor, you put a jacket around it. It literally is like what we do. We don't care how cold it is. We just find the right jacket for the occasion. So that's what this is. It basically gives you an afterthought on the thermal design. It's great. It's effective if you have the space. You also create a second loop. You are now creating another subsystem, which you have to have a pump, a coolant. You have the potential for a leak. So you're creating a secondary system. So if you have a way of doing it passively, most of the time we would prefer to keep it a fan at the end of the motor that pushes the air through. That's much better. Better meaning easier. I'm not saying better like effective. So for traction applications, in almost every scenario, you'll be looking at liquid cooled systems. There are more advanced methods, but liquid systems tend to be where we normally end up starting the design. You want to see a few more? There's a whole bunch in there, right? So, and this is actually from one of the papers by Grunwald and Kern. This is actually published in the Transactions of Transmission Electrification. And I will put a very shameless plug in there because I work with transaction transmission electrification. So we have some excellent papers on traction drives and thermal behavior. If you want to check it out, there have been several of them. A lot of the discussion we've had today are in TT. Go check it out. Submit papers there as well. That was just a plug. That had nothing to do with the shortcuts. But if you look specifically at the traction motor cooling systems, there are different vehicles that have employed different motors and have different cooling methods. So each one of them has considered. Yeah, do you have a question? So your hand. Yeah. Normally you would get it from the auxiliary battery. So you're a typical, at least to my knowledge, most of the motors that I've seen come across, I have to make sure I'll give myself a 10% chance of being wrong, but usually it would be from the auxiliary system. So it will not come from the primary battery, I would imagine. So because the auxiliary system, because you want the heat to be independent of the battery pack, the high voltage battery pack. So it's a much lower power level, yeah. The high voltage battery pack also charges the low voltage battery pack. So there's actually a converter that connects between the high voltage and the low voltage pack. So yes, because your car has to start, right? So in order for you to start, your lights have to turn on, your dash has to go on. So you have to have that auxiliary system no matter what. That's not going away. So you just have to make sure that you have a mechanism that allows you to charge your low voltage battery, because previously you had an alternator that was directly charging your low voltage battery. Now you are allowing your high voltage battery to send power onto your low voltage battery. That's not the case for every car, because if you're in a hybrid, you might still have a connection elsewhere. But generally speaking, the HV pack charges the low voltage pack. That's a good question. So like I said, there's actually if I include that. So right there, give me a second. I'll get there to the next slide. Some of these questions I do anticipate. I don't always get them right, but I try to see what the person is going to ask right after this. So this one I got lucky. I was not that planned, but in terms of the vehicle and the motor type, you can see you have inductions, PMs, really covering the entire spectrum. What you will also see is that majority of the motors have moved away. Like Tesla, if you remember, at the very beginning, the Model S, right? The original one had inductions. And they're talking specifically about how inductions are going to be big, they're going to be important, rare earth free, so on and so forth. And then they switched. They went to PM. So they are now also using PM motors. So they've gone up because in terms of efficiency and performance, PM motors really are up there because you have a free energy source on site. You have a permanent magnet that doesn't cost you anymore. The only challenge is that permanent magnet comes at a cost. Where you're going to get the magnet from, whole another conversation, which is why the emphasis is going more towards generating artificial magnets. So we can eliminate the need for mining of this rare earth material. So if you look at a Porsche or an Audi, you're looking at basically they have either a cooling jacket or you have a water cool system. So they have channels going into the channel slot and they will run through. Or you can have a cooling jacket with a direct cooled motor. So you can have different methods. And specifically, if you're looking at the speeds, you see all of them are above 13,000 RPM. So they're not as high torque dense unless you see the power level, which reminds you that the speed might be high, but so is the torque. So they don't look to be very torque dense only because if you look at the speed. But generally speaking, the only one that I see for air-cooled system here is really going to be this one here. That's a 2015 BMW, which actually has a 65 kilowatt system. It is an air-cooled rotor with an integrated fan cooling. But generally speaking, most of them would have a liquid cooled system that either run the coolant loop through the channel or would have a cooling jacket. So in terms of the passive or active cooling, you have two different ways of looking at it. Passive would basically means you have no major active device. You have no fans, no pumps, it cools itself. You can have options like phase change composites that allows you to absorb the heat, dissipate that gradually. You can have typically this application usable for low power motors. It's not always suitable for high power systems. And the best thing about these systems is that they're more reliable. Why? Murphy's law. There are fewer things that can break, right? So if there's no moving parts, the number of the chances of it breaking substantially goes down. So you can also have things like additive for solid liquid particles. Like I said, you can have gas bubble flows, and liquid trace additives to boiling system, that kind of stuff as well. If you look at active cooling, you do require external fans. You have to force a coolant. You have to make sure what you're designing it for is worth the cost, which means it has to be a high efficiency, high torque application where you are going to get that level of heat. Otherwise, it'll be an expensive solution. So cooling techniques, to your question, right here, we have specifically if you're looking at coolant, depending on what you're trying to accomplish. If you're trying to cool the stator winding, stator core, or the end winding, depending on what you are selecting, you would either go for direct or indirect cooling for the stator core. That's the lamination. For the lamination, you would either have air or cooling water jacket. For the direct cooling, you would have water, oil, or glycol. The ones that oftentimes people are looking at is very interesting to me as well is the end winding. End winding is when you have your windings at the very end, you have the end turns, right? So by definition, copper is a conductor, which means the heat it gets is going to transmit to whichever space has the coolest temperature, right? Heat transfer, basic principles of thermodynamics. So it will transfer to the coolest part of the winding. So if you spray cool the end turns, then what it can do is it will actually extract the heat from there and take the heat into the oil that you're spraying into it. That means all the heat will start moving to the end turns. What are some challenges you can imagine for something like that? By the way, I speak with my hands a lot, so don't get offended if you see my hands waving across in the video or whatever. So what do you think? So what do you think some issues can be if you're doing spray cooling for your liquid jet is one thing. I'll talk a little bit about that as well. If you're doing spray cooling, what can you imagine what could be a problem? You are spraying in the motor. You're actually spraying onto the end windings. It'll form so there's a film. Sometimes a bigger problem also could be it can create a fine mist which actually goes around it. So it can be relatively less. I shouldn't say dirty. It can be a little more dirty, but it's you have to find the right enclosure to contain it. So yes, you can also form a film because you're spraying it onto the end turns. You have to make sure where that mist lands. Wherever that mist lands, you either have to have a mechanism for taking it out, or you have to analyze the impact of what such a system could end up doing. So, all right. So in terms of what we did in terms of the mode of heat transfer, you can also have options like you can have conduction, natural convection, forced convection, radiation, or you can have PCC or evaporative cooling. PCC basically is a phase change composite, which essentially changes its phase when it gets hot. It changes its phase, right? So we work with a company that got acquired very recently, specifically for batteries. It's a company that's called All Cell Technologies. It was actually based on an invention, and the inventor and the CEO was from IIT, and they went into battery manufacturing, and they do this for fast charging systems and such. And they just got recently acquired, and their primary technology is PCC, is phase change composite. Ideas like that, in which basically the idea there is it's got a graphite microchannel. So it's imagine a Brillo pad, like the pad we use for like a Scotch-Brite kind of thing. How do I give it? I'm coming into all of my references from my sector, from my side of the world. But like microchannel, like what you use for brush scrubbing your containers, the brush. You know what I'm talking about? The metal brush that we have always grown up with. That's kind of microchannel. It basically has that a mesh of wire. Imagine that wire, which is very light, and you pour paraffin wax into it. Paraffin wax is what? Candle wax. So you create now this wax, this microchannel is made out of graphite, pencil lead. So pencil lead is also very light. You create a microchannel with graphite, you pour paraffin wax into it. What that does basically, it creates this mesh. It's like not a honeycomb. It's a very complicated mesh inside of wax combined with graphite. When you insert the cell into it, the heat is transferred onto this wax. Graphite has high conducting properties. It transfers the heat onto the wax. That wax starts to melt. But because you've created microchannel, surface tension stops it from collapsing, much like a candle. It doesn't collapse down. When that happens, that basically your wax starts to melt. Once the entire wax is melted, you have a problem. But until such point that the wax entirely melts, it can absorb the heat and manage to not have a catastrophic failure. Once the heat is gone, let's say it was a peak power draw of 30 seconds or whatever it is, now the peak power is gone, it can recongeal, become wax again. And once again, you've done this with candles in your house. We do this all the time, right? You use a candle, it melts. When we turn the candle off, it's right back to being solid again. Same idea. Arguably, not arguably, actually this one has a theoretically infinite life. It can keep melting and congealing and for an indefinite number of times, no moving parts. So that is very useful, except until you end up melting the entire wax, in which case, so you have to plan it out properly. You have to do CFD. You have to specifically design the system to make sure it can handle that amount of temperature properly. So this was actually an air-cooled motor that we did, and when we look at the air-cooled motor, this was I still don't have an answer to your question about how much air heat we got out of this. So CFD design, you can have different enclosures specifically that you talk about NEMA standards. You have open drip proof. And I'm within 5 minutes. You have totally enclosed, non-ventilated, fan-cooled, wash-down enclosures. So there are different standards you can look at for what kind of enclosure you would use for from the design perspective. You can have either dust-proof, you can have waterproof, you can have motors that you can put inside the water. So you don't want to put everything everywhere because they don't work like that, right? They're not, the enclosures are not designed specifically. You can also have an explosion-proof, which by definition means the rest of them are not. So you don't want to test out what happens when, because things go really wrong really quickly. So you can actually have for liquid cooling, you can have forced liquid through a machine. You can typically use oil, water, or glycol, and thermal management oftentimes requires the press-fitted water cooling jacket around the stator. It can be limited by size and weight. We did this case study in specifically, there you go, actually, I got the answer here. So we had the table. I didn't know if I had the table here or not. So we had an 80 kilowatt peak, 25 continuous. We had an accumulated pack limiting our size, and we wanted a peak power for less than 10 seconds. And the current limitation was about 75 amps from our DC link. What we found basically, we analyzed different cooling methods specifically to your question about what temperature we observed. We saw that if we did water cooling plus different epoxies, we got the lowest temperature. Actually, no, sorry, water cooling with potting was lowest temperature, in which you have a potting material in it. And the least effective was, of course, air cooling, as we can very well expect. Water cooling was not as effective as doing a hybrid cooling method. And that was our big takeaway from this entire process. So what we observed, and this actually lines up with what the studies have shown, is that if you actually, depending on what kind of application you use, which once again from Grunwald and Kern, the previous paper had shown you, they show you the complexity of the cooling system as a function of peak power and powertrain weight. So it tells you what system or what solution could be most effective in specifically identifying specifically in the context of your application. This is a quick example here. This is for the 2012 Hyundai Sonata cooling system. We have an external PM motor that's driven by a pump, which is used in addition to an internal shaft-driven pump. So idea-wise, a different way. So here are the cooling, basically the flow paths. It goes from the outside. There's an inlet and outlet connected to the shaft or to the housing. It allows your heat to be extracted from the motor. So with that, I'm going to stop here, and I'm going to just quickly ask you, if you're talking about optimizing efficiency, is it effective to look at the overall drive range? Do you think a co-design method, I'm almost sounds like I have tried to convince you this whole time that co-design is important, and now I'm asking you, do you think co-design is important? It sounds like an unfair question because I've tried to convince you for this long. But with that said, I'm absolutely open to people feeling like, no, you know what, our method works, and that's totally fine. And does drive cycle give you an informational idea about what this drive cycle or duty cycle, right? You can also have a thing of it's going to operate for 75% duty, which means it's going to operate for a lot longer than it's going to not operate. So on time is larger than off time. And also, do you have any software tools that you typically would use for applications like this? I'm going to stop here, but I'm open to some questions if you have any. And I'm going very fast. I fully recognize that. I'm speaking very fast. These topics are very interesting to me. I think these are the most unique perspectives, not because I'm doing this, but I'm doing this because they are so unique. But the ideas really are very fun to do, especially when you start exploring these topics in collaboration with mechanical engineers, with applied mathematicians. The scope of your research dramatically gets better. Because all of a sudden you are going into spaces. I work with electrochemists on batteries. I work with mechanical designers with hydraulics. I work with mechanical design and thermal management, applied mathematicians and modeling. And that is, in my mind, that's the future. So for your PhDs, research and everything else, I strongly encourage you to seek out another faculty that you perhaps, in consultation with your own faculty advisor, of course, talk to somebody who might kind of broaden the horizon, broaden the scope of your research, and gives you an idea that goes beyond what you could have come up with if you had the right equations. If it's a plug and chug kind of thing, you put the numbers in and you get the right answer out. Did you truly move the needle when it comes to innovation? That's always the question. Because in the process, you never know when you might end up with a Tesla. If you are looking at motor companies, one of the ones I would encourage you guys can check out is a university spinoff called YASA Motors. They're actually based out of UK. And they came out, they had one of the most power dense motors. I don't know if people have overtaken them or not for a fact, but YASA Motors, actually, they make traction motors. They had axial designs, and they claim to be best in its class generally. So you never know when you might have a solution that actually makes a lot of things possible. So on that note, guys, thank you very much. We'll take a quick break, and Professor Ragan will tell us when we're supposed to come back. 2 p.m. we'll be back. It's right now it's 12:40. We'll be back at 2 p.m. guys. If you have any questions, shoot them my way. Thank you so much.